Okay, I want to welcome all of you to the second day of the Access workshop. Today, actually, the focus will be on experiments which we did at Sector 30, mainly the helix and nuclear resonance scattering. I want to thank all the speakers for presenting today, and I think we can go ahead and start. So the first couple of talks will be an update about the beamline and about the APS-U coming, and Ahmed Alatash and Michael Hu will start. So Ahmed, please go ahead.
Thank you, Ayman. So today I'm going to talk about this upcoming APS-U and Sector 30 beamline update, particularly for the helix spectrometer. So as we know, APS Upgrade is finally here, and in a nutshell, basically last scheduled user operation is just ended last Monday on April 17, and we are now in a transition week, and the decommissioning and installation period is scheduled to start next week. The upgraded APS ring will return to operation after 12 months of installation and commissioning period. During this time, electron storage ring will be upgraded to new powerful MBA lattice that incorporates the about 1,300 powerful new magnets assembled into 200 modules outside in a warehouse, as shown in this picture on the lower right side. And the regular updates can be followed on this website. So as I said, yeah, there is something on my screen. Let me just remove that. Okay, I got it. So as I said, APS Upgrade is a next generation facility that will replace the current electron storage ring with a new, more powerful MBA lattice. And new ring is particularly optimized for the hard X-rays and has an increased coherent fraction of the beam, and the round source shape is ideal for imaging. The expected gain at Sector 30 after APS-U can be summarized as follows. It will greatly help improving the beam size, especially in the horizontal direction. This is good for the high pressure and thin film studies. On the other hand, flux on the sample will not go up greatly as the brightness due to change in the storage ring going down from 7 to 6 GeV. We expect to have about 50% increase in the flux on the sample. As for the increased coherent fraction of the beam, so far we did not come up with any good scientific application for the phonon studies. All of your inputs are welcomed here today regarding this subject. If you have any good idea how to take advantage of this coherent fraction of the future beam, we can accommodate as one of the early first science experiments during the commissioning period. As you know, helix spectrometer works at single energy at Sector 30 beamline. This allowed us to use very specific short period undulators as compared to standard APS undulators. APS-U will also provide special short period undulators that will be serving both our programs at the beamline with moderate flux gain on the sample. As part of the APS upgrade, they are going to build 8 new beamlines as shown in the green colors here. And the several other existing beamlines will be enhanced or improve their capabilities. Though some of those enhancement projects are currently descoped until further notice. 30 ID beamline is initially granted to enhancement project to provide better temperature and energy stability at the beamline. First project involved cryogenic conversion of the causal monochromator in A station. Luckily, it was procured and installed last May before this project halt happened. Currently, it is providing week-long stable beam and flux onto high-resolution monochromator. Second project is a new all-in cryogenic high-resolution monochromator based on the recent design by Tom Toner. Even though design was mostly done, currently it is on hold. On the other hand, there is a good possibility of reactivating these scope projects via DOE's MIE project funds in the near future. We have resubmitted our upgrade of the cryogenic HRM project. In addition, we are asking new mechanical band KB mirror to replace the existing 15 years old bimorph mirror systems. When purchased, it is possible to have about 1 micron beam size both direction based on the ray tracing. If not, this is not a showstopper at the beamline. We will still have improved horizontal size due to the round source shape. Now let me switch gear and talk about the current capabilities at the beamline. We are constantly working on extended sample environment for different experiments. At ambient pressure, we can cover the temperature range from cryogenic temperatures up to about 1000 Kelvin by using cryocooler or the heating stages. This ARS cryocooler has become a standard setup at the beamline for most of the experiment. We can also access to high temperature up to about 100 GPa and high temperature by using externally heated diamond anvil cell. High pressure and low temperature experiments can also be done by using the cold hat from Sumitomo together with the membrane diamond anvil cell. So also, there is a growing demand to study phonons in thin films in order to understand the confinement and the interface effect. This is important in designing new technologically relevant materials. For this reason, we extended our beamline capabilities to grazing incident IXS by taking advantage of our small focus beam size. We are working with several groups in this subject, and the first publication in this subject just published recently in collaboration with Ming-Da Li from MIT. Even though current beam size allow us to work on the thin films, we are aiming to go down about 1 micron beam size in the near future. Recently, we also extended our IXS measurements under magnetic field by using a permanent magnet developed in collaboration with undulator groups. It can be used inside the cryostat, and the magnetic field direction can be aligned to in or out of the scattering plane or any crystallographic direction as shown in the picture on the lower right side. Studies are underway with promising results to come. Later today, Ming-Da will talk about these measurements. Also in this last cycle, user-provided razor bill cell is used in IXS measurements in which the sample is strained. These studies are underway in collaboration with Stanford University and 6ID scientists. And today, Anisha will talk about the details of experiment later today in the workshop. So now let me finish up with the timeline of the APS-U startup that we are all waiting for. Accelerator commissioning will start in January of 2024. During this time, they will commission the brand new ring with current up to 25 milliamp. Later in May, beamlines will start receiving the initial beamlines mainly for the shielding verification. They are anticipating about 2 beamlines per day, taking up up to 2 months to bring all beamlines online. And beamline technical commissioning and scientific commissioning will continue about 1 to 6 months until December 2024 for most of the beamlines. As for specific to sector plan to sector 30, we plan to once we are enabled for the beam, we plan to finish up the commissioning in 4 weeks, and immediately after start with the scientific commissioning. During this time, we are looking for high impact first experiment with passionate and patient users, since the ring current is going to be at 50 milliamp at that time. Feel free to contact with us with your ideas. And with that, I would like to conclude my talk, and thank you for your attention.
Thank you, Ahmed, for your talk. If you have any question, I would wait until the end of this talks, basically, because we have to move to the second talk. Michael, would you please go ahead? Michael?
Sorry, I was muted. So now, do you see the screen now?
Yes.
Okay.
Can you put it in present? Yeah.
Okay.
Okay, thank you.
All right. So welcome, everybody. So I'm going to talk about nuclear resonance at 30. You may ask, why nuclear resonance at 30 ID? Well, the obvious reason is a technical, because the two programs share very close energies. So the silicon reflection used in Herrick's, and then this tin resonance. So, but a deeper connection actually is physics. It's the lattice dynamics, because a big part of nuclear resonance program, and actually most important application at a synchrotron is this NRIX, this inelastic scattering. So that study phonons, lattice dynamics. So that's why. And then also there's a complementary study. You know, if you measure dispersion and denser states, you can learn quite a bit about this acoustic phonons. So that's why. And then here is the team, nuclear resonance people, and then we have a Sector 30, Ahmed Ayman, and we have a high pressure and the diffraction experts, and then technical support and the administrative support. So this nuclear resonance technique is ubiquitous all over the world in all the major synchrotron, third and the second, third and the fourth generation sources. So APS is part of that. And then actually this Beijing synchrotron is now, they have a, they're moving forward. So the picture is very different now. And then they recently, I heard they have a electron beam in the LINAC already. So here's briefly the nuclear resonance program at APS. We have several isotopes, and then you see tin is at 30. And then this is how it's done. The experiment, the critical components are these high resolution monochromatometers, and then the APD detectors, and then of course it relies on timing. This is a timing trick to detect the nuclear resonance signal only. So that's the big advantage. So and then this we have a roughly briefly the two major techniques, two major methods within nuclear resonance. One is forward scattering, the conventional, similar to conventional most-power spectroscopy. There, we can study electronic structures like valence, magnetic field, things like that. So and then the inelastic part, which is only possible at the synchrotron, developed since the 90s. So you can see you study all this dynamics, atomic lattice, and then sound velocity, and then we can reduce get denser states, which is very important study in many fields. So that well, you all know that. And then there's certain quantities or properties you can derive from the spectrum or the density of states. So a little bit fun fact about the tin. So it's an important element of both fundamental and then applied importance. And then actually you see that it's the part of a bronze. So it's been a technological material since the very beginning. So now it's component in many new materials. Actually, later Willie is going to talk about this Kagome magnets, Kagome lattice materials. So it's a little bit about the properties of nuclear resonance. The important thing is I call attention to is this lifetime. It's shorter, much shorter than iron. And then, so tin is one of the favorite in terms of, well, not in favorites in application, but also in terms of how to say, the easiness to get a signal. So the signals can be very strong. So here is the tin program at APS. It started before APS even operational. So I think this first experiment with tin nuclear resonance was observed at the JES. And then I did my PhD there. And then in the 2008, when Sector 30 was built, we have that in mind actually. And then the nuclear resonance was used in calibrate this high-res mono. And then in 2014, the program moved to 30 because we have a factor of 10 flux. Why wouldn't you do it there? And then at the end of that year, it becomes a user instrument and accepting GOP since. So a little bit technical. So you see the energies are very close, the Herrick's energy and as well as the tin energy. So the mono and then flux and then the focus. And this focus will get better in the APS-U. So it's a little picture about the station. So the nuclear resonance program is in B station. So we have this monocrometer and there's a little close up there, and then the mirror, and then the showing the high pressure setup as well as the low temperature setup. So there's just things have been done, and it's across a wide range of things, and then with many sample environment conditions. So what do we expect at APS-U? So you all heard about this timing mode and things. So 48 bunch mode is not a problem for tin because, as I show you, it's a short lifetime. So it's 77 nanoseconds, still good for nuclear resonance, for forward scattering. Inelastic, it doesn't affect it much anyway. So, but in terms of flux, as Ahmed has said, flux doesn't really change much. So because the lower of the electron beam energy and then the undulator selections. But it's a lot better than high pressure experiment. The reason is currently we don't have a long horizontal mirror, so that actually currently we are losing flux. We would just throw half away. So now with the new beam, that part gets fixed. So automatically we can double flux for high pressure experiment. And the focusing is a lot better, particularly in horizontal. But with the current mirror, I mean, vertically, we don't expect much. So the focus will be around 10 microns, things like that. But horizontally will be on the same order. So hopefully we can, as the Ahmed said, we can get a mirror for this program as well, can focus down to like 1 micron. But with that, also we have to consider the mono, the high-resonance mono, because that has some implication as well. So challenges, as always, the sample environment, detectors, electronics, and data, and all that. So So a little bit about, Ahmed talked with already, but I'm more focused on the timing possibility. So basically, the user or some scientific experiment can be done starting next summer, the second one, but current is limited. 48 bunch is probably well, it's questionable anyway. And then, but the accelerator division, and then they are pretty confident that they can start like fall. They can run more timing mode, and then going on from there. And then currently they're saying with this the limitation of the bunch current, so the 48 bunch is going to limit it to 130 milliamps, even though the ring will be at 200. So that's, but that is they're being conservative. Because they tested, they think they can do this already, but obviously they're going to push to go higher. So that's a little bit timeline of when we come back. So with that, I will thank you.
Thank you, Michael.
All right, so let me just stop sharing.
Okay, so we're gonna start our first scientific talk. Olivier Delaire from Duke University. Olivier, please go ahead.
Okay, can you hear me okay?
Yes.
Great.
Thank you.
Screen here. Do you see the slides?
Yes.
Perfect.
Do you want to put it in presentation mode maybe? Because
Is it now?
no, it shows all the slides.
All right,
So,
like this?
yeah, that's better.
Perfect.
Thank you.
All right, good morning, everyone. Great to catch up with this interesting development at APS, and great to see everyone. So I'll be giving you a quick update, and for those of you who are not familiar with the work of my group, a little bit of a broader perspective. But generally, we're interested in so phonons that are not good phonons, I would say. So phonons that are substantially impacted by strong anomalicity coupling with other degrees of freedom, for example, electron phonon coupling, spin phonon coupling sometimes. And we combine access studies with a lot of modeling we do in our group, as well as other scattering techniques, neutron scattering or diffuse scattering. So I'll show examples of how this can be useful. First, I'll start by acknowledging students and postdocs who've led a couple of projects I'll be highlighting today, and of course, collaborators, particularly at Argonne at Sector 30, but also in the Material Sciences Division, since we had very good collaboration ongoing with Ray Osborne and Stefan Rosenkrantz, as well as Matt Krogstad, who is now beamline scientist at Sector 6. So a brief outline of the presentation, and I apologize, I probably won't have time to talk about the last topic. So I'll be mostly focused on studies of very unusual phonons in metal halide perovskites. These are interesting materials from the point of view of energy applications, but there's also quite interesting fundamental phonon science associated with those materials. And then hopefully I'll have time to touch on the topic of thermal transport in thermoelectrics. So the underlying sort of perspective we have when we do these access studies and generally phonon spectroscopy is to try to understand effects that go beyond the standard phonon quasi-particle picture. We all know that if we have a harmonic system, we have well-defined excitations in terms of lattice vibrations. So collective modes that define quasi-particles are long-lived, and those are distributed on underlying dispersions. We can compute this from DFT nowadays. That's become pretty routine. However, there are strong anomalic effects, or important anomalic effects that often develop in real materials as you increase temperature, for example. You can hope to understand this in the framework of the damped harmonic oscillator. You can extract phonon lifetimes. I think Michael Manley will focus on this topic in the next talk, and that connects with thermal transport. I'll show a little bit on the thermoelectrics. However, there are some I would say perhaps less well understood, but very interesting effects that happen when you have very strongly anharmonic potential energy surface in softer, somewhat floppy materials. And there we really lose the intuition of this quasi-particle and Lorentzian peaks in the spectra. We can have very complex many-body effects in the spectral functions that we can start to hope and understand based on more advanced modeling, and I'll show a little bit on that. In extreme cases, you can lose vibrational dynamics entirely and have more of a relaxational behavior that then shows up at very low frequencies. And we indeed see some of that in the meteorite perovskite, as I'll illustrate in this presentation, and also in materials such as superionic conductors that we're also working on, but I won't have time to discuss today. So let's focus on the meteorite perovskites first. So a lot of you have heard about these materials. These are materials that are attracting tremendous interest for the past decade or so, as it was realized they can make very good photovoltaic cells that are now rivaling the efficiency of conventional silicon photovoltaics. They're potentially useful for other optoelectronic applications, LEDs and such, or radiation detectors. And it's been known for some time that these materials are a little strange. They are crystalline, but very soft and strongly anharmonic, so very different from silicon. They have very low thermal conductivities and actually candidate thermoelectric materials also for that reason. They also have very large thermal expansion coefficients, very large mean square displacements, very low elastic constants. And it's starting to be appreciated that these peculiar lattice dynamics are very likely important to understand the electron phonon coupling and the photocarrier relaxation with the lattice. But we don't have an electron phonon theory that's currently able to describe coupling of electrons with excitations that are not well-defined phonons. So there's actually a lot of developments in this area, but we need to start by better understanding the phonons in this kinds of very anharmonic potential illustrated in this cartoon at the right here. So we've investigated a number of these meteorite perovskites, focus on cesium lead bromide and then a double perovskite version next. So cesium lead bromide is effectively the simplest member of this family. You can consider it a parent structure. There's lots of interest also in the hybrids where the cesium ion can be replaced with organic cations such as methyl ammonium. But this provides us a little bit simpler structure to hope and understand the unusual anharmonic lattice dynamics. And so it's a perovskite. So at high temperature, you've got the typical cubic perovskite structure. And upon cooling below 400 Kelvin, there's glazer tilt systems. So lead bromine octahedra tilts that distort the structure into a tetragonal space group here. And then further cooling a few tens of Kelvin, there's further tilts superimposed, leading to an orthorhombic structure. What's very important, and perhaps the main message of this study, as I'll show you, is that these crystal structures shown here are really just time and space average crystal structures. There are very large fluctuations that actually modulate this average crystal structure and are indeed related to the phonon dynamics and are important to understand the electron phonon coupling. But if we stick to this simple sequence of crystal structures here, these, as in all the oxide perovskites, are understood in terms of phonon eigenvectors of the high symmetry parent structure. So for example, the M-point phonon for this tetragonal distortion and R-point phonons for further orthorhombic distortion, okay? So I'll start by showing you what I mean when I said there are strong fluctuations away from the average crystal structure. So this is revealed in diffuse scattering. And so one of the main points of my talk is that it's very useful to couple inelastic studies with diffuse scattering studies. And we see that directly here. So if you look at the cubic phase of the cesium lead bromide in a plane L equals a half, there are no Bragg peaks, but you still have a lot of scattering that's got pronounced structure. in the form of these rods that actually follow the edges of the cubic Brillouin zone. And these rods partially condense when you go into the tetragonal phase at the endpoints, but there's still some rod-like signature that persists. Finally, in the orthorhombic phase, you largely have sharp bragg peaks corresponding to all the superstructure bragg peaks of this larger cell here, and some remaining thermal diffuse scattering. So we see these diffuse rods both in X-ray and neutron diffuse scattering. So the X-ray work was done in collaboration again with Matt Krogstad. And then that's not letting me change here. Okay, so if we have rods in reciprocal space, this indicates we have two-dimensional correlations in the disorder away from the average crystal structure in real space. However, from the diffuse scattering, we don't know because this is energy integrated at this point, whether this is static or dynamic. And so I'll show you these are actually fluctuating, deviations from the average crystal structure corresponding to correlated or collective lead-bromine octahedral rotations. All right. So quickly, let me show you, if I can get this to run here. The diffuse scattering is obtained from sector 6. So we get these really nice volumes of reciprocal space here that show that in the planes that are half integer, we systematically see these beautiful rods of diffuse scattering here in between the integer planes where we see the bragg peaks. All right, so we can take three-dimensional views. This is actually from the neutron data at the top here, and you see that indeed the diffuse scattering forms these rods. And so from doing the spectroscopy, as I'll show you in the next couple of slides, we can actually interpret this rod as coming from overdamped phonon modes along the edges of the Brillouin zone here. So, so we've done neutron scattering and inelastic X-ray scattering on the double perovskite that I'll show next. But the neutron scattering was done first on this compound here, and it allowed us to see that when we focus on the edges of the cubic Brillouin zone, we find that there's a completely overdamped phonon branch that is derived from the zone boundary acoustic phonon modes in the structure. But if you look away from the zone boundary, you'll find that there are still sharp acoustic phonons. Okay, so, but the thing that's really peculiar is that in a lot of oxide perovskites, you may see soft modes at high symmetry points like R point or M point. In these materials, and I'll show you this is happening in the whole family of halide perovskites, you see this kind of overdamped quasi-elastic response at a continuum of wave vectors all the way between M and R, so that means along all the edges of the cubic Brillouin zone. And so it's really a kind of liquid-like type of dynamics for these wave vectors. So you've got this fluctuating two-dimensional sheets of lead-bromine octahedral rotations in real space. I've got this overdamped liquid-like behavior. Yeah. And using our modeling, we can actually reproduce the diffuse scattering as shown in the top half of these panels compared with neutron data. We see the sharp rods at low frequencies and the more conventional thermal diffuse scattering at higher frequencies. We can also use the modeling to understand why these materials do this. In short, this arises because of their unusual anharmonic potential energy surface and a competition between these two types of distortions that have got very similar energetics in our simulations, and also large amplitude fluctuations with well depths that are consistent with the phase transitions being around room temperature. We can go further than these types of potential energy calculations and do full MD simulations. I'll show you also some more recent work where we do a lot of machine learning MD simulations, which is going to be very useful to further investigate the stronger anharmonic materials. So I mentioned we see this type of behavior in the entire family of the halide perovskites. This is some unpublished works here that show this. So I'll focus next on the double perovskite system, which is lead-free. So this effect is not necessarily associated with having lead ions, as is sometimes claimed. And we also see it in a hybrid systems, and that's, by the way, also reported by other groups now. So I think there's a work that's published, almost published, from Mike Toney and Dmitry Resnick, where the same rods of diffuse scattering are observed in methylammonium lead iodide and lead bromide systems. So this is really quite general in this family of materials, and this is really further motivating more advanced studies of electron phonon couplings and complex dynamics. So let me say a little bit more now on the double perovskite system that we're studying with diffuse scattering, IXS, and neutrons also. So, so this system has got silver and bismuth ions on the B side. These are ordered in a rock salt arrangement as shown in these plots here. And you still have the tilt systems of the bromine octahedra here. And so you've got a tetragonal distortion that now occurs at a little bit lower temperature, around 120 K. So we see the similar rods as we've seen in cesium lead bromide earlier, because there's effectively a folding associated to the larger unit cell, so smaller Brillouin zone. The rods are still along the edges of the parent simple cubic perovskite, but they are now going through some zone centers of the double perovskite notations. The correspondence between double and single perovskite is shown in these plots here. It gets a little bit complicated, but okay, I'll try to simplify it for you. So the main point is that now this actually goes through some zone centers in reciprocal space. Okay, and so we can do our modeling in the systems also. We can reproduce the diffuse rods, and now because this is happening through the zone center, so we actually find that this is now associated to a low energy transverse optical branch, which is strongly overdamped, as we can compute now using full calculation of SQNE using machine learned interatomic potentials and large scale MD. So this these types of simulations have really come a long way in the past just a few years. It's moving quite fast. So we've been using this successfully in these systems, and we can now compute the full dynamical structure factor, including anharmonicity to all orders, you could say. And we see that there are some well-defined acoustic phonons in those systems, but you also have this strongly overdamped low energy transverse optic branch. And I'll show you that we do see that in the RX measurements. We can also decompose the diffuse scattering signature in terms of contribution from various elements. And we find that indeed, it's mostly associated with the halides in the structure. So let's look at the spectroscopy with HERIX to see if we can confirm these predictions here from machine learning potentials. So we looked at a small crystal. This was done fairly recently, back in December. Still some analysis of the data that's going on, so the figures aren't as polished as I would like at this point, but we see the main points. So on the left here, I'm showing you some spectra that show that indeed we have well-defined transverse acoustic modes here at all temperatures we've measured across the cubic to tetragonal distortion, which is 120 K again. But if we look on the rods, so if we pick reciprocal lattice vectors where the rods are intense, we find that at high temperature, there's indeed this very broad signal. It's wider than the energy resolution of HERIX. You can see that it extends over several milli-electron volts here. It's got this kind of almost plateau-like shape that extends about 2 to 3 milli-electron volts. And when you cool down towards the tetragonal transition, this picks up intensity and somewhat condenses. But the weird thing again is that it doesn't condense at a single wave vector, but rather all wave vectors along the rods. And then when you cool down across the phase transition, this gets a little bit weaker, but persists for some range of temperature. Now, there's a further effect that we've discovered in this double perovskite, and that was quite surprising, is that the ground state is not what has been reported to be. It's not just the simple orthorhombic structure I showed earlier. We've found in the diffuse scattering data, as well as neutron diffraction, and as I'll show you with HERIX also, that there's a further modulation that appears below 40 Kelvin or so. And so you find these quartets of superlattice peaks here systematically across reciprocal space. We can understand those in terms of a soft phonon in the tetragonal phase around the K point, as is shown in this calculation here of the tetragonal phase. And indeed, we confirmed this based on the recent Herix measurements. So let me show you this. So again, on the left here, we have the prediction based on the anomalic calculations that show that as you cool down in this tetragonal phase, you expect to see soft modes around the K points. And you can expect this would condense around 40 Kelvin or so. So if we measure at 20 Kelvin below the phase transition, so the phase transition is observed. We see these relatively weak, but still clearly observed superlattice peaks here around the K point wave vector. It seems to be actually slightly offset from the exact K point, which would be 2.75 and 3.25. I think the figure is slightly shifted here also, so the coordinates need to be adjusted probably, but the actual wave vector of the distortion seems to be closer to 0.2 and might actually be incommensurate. So we're still working to confirm this. But if we look at the spectrum here from Herix close to this K point, we find that above this, so again, this distortion occurs at around 40 Kelvin. So if you're at 100 Kelvin, you see well-defined phonons at finite frequency here. At 50 Kelvin, you're getting very close. This is nearly condensed here in the orange trace. And then below the transition, you then get a superlattice peak effectively at this modulation wave vector. Okay, so I just have a couple of minutes left, I believe. So I'll have to go through this next topic of understanding phonons in thermoelectrics to understand thermal transport relatively fast, and I apologize for that. So this is a study we've done a couple of years ago here, looking at this relatively new composition of thermoelectrics that have attracted a lot of interest in this community because these are based on magnesium and generally a pretty cheap composition, and they actually work well around room temperature, so they could displace some of the conventional bismuth telluride type thermoelectric materials. And this composition M2X2, where the B side here, if you will, is magnesium, and the A side could be magnesium or some other element, as I'll show you, are based on this so Zinto structure. This is a calcium aluminum 2 silicon 2 crystal structure, and we'll see that the difference between the magnesium 1 site and the magnesium 2 site in cyan here is important. And so depending on ions you put on a magnesium 1 site, if you replace this magnesium with other elements that are larger, you can strongly modulate the thermal conductivity. But this figure here is just showing that indeed they're already achieving high thermoelectric performance. And this is in part because they have very low thermal conductivities, as is illustrated here. So if you look at the magnesium 3 antimonide, it's got comparable or lower thermal conductivity than much heavier elements, lead telluride or bismuth telluride. So this is plotted on the density axis here at the bottom. You can see this is half the density, but similar thermal conductivity. And very strangely, when you replace the magnesium on the magnesium 1 site here with a heavier element, such as calcium, you actually get a big increase in thermal conductivity by a factor of 3, which is quite unusual. You would expect that heavier elements should lead to lower vibrational frequencies and thus lower go velocities and thermal conductivities, but that's opposite to what's observed. And so we started with some powder inelastic neutron scattering measurements to look at the phonon DOS, and we see that indeed when we replace magnesium with calcium in the magnesium antimonide, or magnesium replaced with ytterbium in the magnesium bismuthide here, we systematically see, so going to the heavier element, we see a stiffening of the low energy part of the phonon density of states, which is quite strange. And so to really understand where this is coming from in terms of the dispersions, so we did the DFT simulations. So my student Jingshuan performed DFT in these various compounds here, binaries and ternaries. And then we actually measured this with Herix on some small crystals. And what we find is that when you look at the binary, so magnesium being both on both sides, 1 and 2, you find a very soft transverse acoustic phonon branch. And when you substitute the magnesium 1 with ytterbium, which is much heavier here, you actually find a stiffening that's quite pronounced for this TA branch. And so this is really the origin of the modulation of the thermal conductivity. We see that in the antimonides as well. And so the student Jingshuan did a really fantastic job in really extracting which interatomic force constants are impacted by this substitution between magnesium and calcium, and found a very large effect in a specific bond that connects the magnesium 1 site with the antimony site here. And so based on this modulation of the phonon dispersions, you can really understand the phonon scattering phase space. Predictions of the line widths here are also increased by a factor of 3 when you go from the ternary to the binary, which is again very surprising, but matches very well what is observed in a measured thermal conductivity. So this line widths are still not that high, so it's hard to really capture this with Herix, I would say. But the effect is already well understood at the level of the phonon dispersions themselves, and the phonon dispersions are actually quite important to understand the scattering phase space. So what are the allowed phonon-phonon coupling terms and scattering transitions? So I'm running out of time. I'm a little bit long, I'm sorry. So I'm just putting my concluding thoughts here. I think smaller beams will be quite useful in terms of looking at smaller crystals, but also finding good spots to do measurements on the crystals, which is sometimes still a challenge. And of course, looking at thin films, samples under pressure. I also believe that we'll have more and more of these, combined studies where we do not just spectroscopy, but also diffuse scattering, and certainly systematically integrate this with advanced modeling, especially based on machine learning. So I'll be happy to take any questions if you have any.
Thank you, Olivier. Any question? I think we're gonna shift everything by 5 minutes since we started a bit late. So we have 1 minute for questions if you guys have any. Okay, if not, I don't see any. Then we're gonna move to Mike Manley from Oak Ridge National Lab. Mike,
Okay,
go ahead.
thanks.
Thank you, Olivier.
Ayman, I hope the speakers will stay at the end of the session, right, to have conversation.
Yes, I hope so.
Yeah, I have a couple of questions to Olivier, but I was thinking that I will ask them at the end.
Okay.
All right, does that look correct?
No, I mean, it's
No.
showing all the slides somehow.
Okay. Now?
Yes, but it's still small for whatever reason. I mean, at least we see single slide,
Oh,
at least on my screen.
yeah, it's probably because my screen is wider.
Okay,
I don't think there's much I can do about that. Okay, so yeah, I'm going to talk about phonon dispersion, lifetimes, and thermal transport in nuclear fuel materials. IXS has been very important in the measurements of lattice dynamics in actinides for a long time now, since in many cases there's problems with isotopes or as far as neutron scattering, the traditional technique. But for thermal conductivity, it's actually a fairly important property in the operation of a reactor. The thermal conductivity controls the fuel temperature, which impacts constituent redistribution and phase decomposition and other things that are going to affect the performance of the fuel. And furthermore, it degrades under irradiation. So over time, the thermal conductivity decreases, and we would like to understand the mechanisms underlying that. So a comprehensive understanding of how irradiation impacts the thermal properties is needed. Furthermore, if you are going to look at thermal conductivity, you need the entire dispersion curve. I think generally people understand this, but just for illustrative purposes, I have a little cartoon here which shows if you start with it's just a simple acoustic phonon and you try to piece together the parts that you get out of the dispersion curve, you can get, of course, group velocities from the slope, you can get lifetimes from the width, and from that you can also get a projection of the density of states, which is related to how much heat is carried per mode, per section of the branch, and then you can multiply these all together and you get something that gives you an idea of where the thermal conductivity lives in the curve, and it kind of lives over the entire curve. You can't just look at the edges of the curve. So you really need momentum resolved inelastic scattering, whether it's with X-rays or neutrons. I want to do a quick overview of different scattering techniques and their advantages and disadvantages. So for inelastic X-ray scattering, of course, you get the smallest crystal size possible. You get okay energy resolution. You typically get higher Q resolution, which can be very important if you have really steep dispersion curves when it comes to getting widths. And of course, because of the small samples and also the fact that you're not scattering from nuclei, it's good for extreme conditions with like irradiated samples or also for pressure. Time of flight neutron scattering, which we use as well, it's complementary. The good thing about it is so the bad thing is you got to use large crystals. So if you want to you do something highly irradiated, it's very difficult. But you can get in principle you can get higher energy resolution, and you get a broad view of momentum and energy space. So it's good for doing sort of comprehensive studies of like getting all the modes, and it's good for finding things because you just get a big view of everything. Triple axis is nice. It's probably the fastest is sort of doing parametric studies. You can get data pretty quickly, but it also requires large crystals, and it only views a small amount of momentum energy space. And then, of course, finally, using time of flight, powder, neutron scattering, you get density of states, which is best for like thermodynamic quantities, the density of states and things like that. And so to get a little more detailed, so when we're talking about actinides in particular, they have very short X-ray attenuation lengths, of course, because of their high density, which means that you're not going to scatter from a lot of material to begin with. So it's well matched to using X-rays on small samples. So your attenuation length, like for example, I got uranium shown here, is something on the order of 10 microns for the energies that you're going to be looking at on Herix, and which compared to centimeter scale for the neutron experiments, and so you can use you can use very small samples, and if you have a focused beam, it works even better, and so it's well matched. So as far as phonon measurements in irradiated samples, there isn't a lot. There's some current some available inelastic X-ray scattering measurements on irradiated nuclear fuels, but they're in thin film form. So we wanted to try to do some freestanding crystals, and so we ended up choosing this uranium zirconium alloy. It's just a promising metallic nuclear fuel for next generation fast reactors, and we looked at a comparison of pristine UZR2, or it's 58% zirconium. It's 2.6 atomic, and it's and then we irradiated it with protons. Now the advantage of using a small sample here is you can't really irradiate a bulk sample with protons. They don't penetrate very deep, and so this allows you to cut. Well, they do, but you get gradients and things. But this allows you to we could slice out a small section of it, use that. We had to, of course, encapsulate it. This is a picture of the sample, which is a little postage stamp. It's about 50 by 50 microns and about 10 microns thick. So it's well matched to, the attenuation length for the beam. We had to actually doubly confine it, and 2 tubes of Kapton, and epoxied at the end. It's a bit messy and it's a little bit difficult to find the first time, but it's sitting on top of a graphite fiber. And so, yeah, so we measured the phonons in both irradiated and pristine samples this way, and did a comparison. So it's interesting. It's sort of a complicated thing. So if you look in certain parts of reciprocal space, particularly sort of in the middle parts of zones, like, so this is at 0.202. So it's a transverse phonon along gamma to M. It's sort of in the middle, and there you see a pretty large broadening with the irradiated sample compared to the pristine sample. So the irradiated is the red, and this is on the left, and the pristine is blue. Whereas if you go towards the zone center, the longer wavelengths, you don't see as much. So whatever the defects that we're forming, which I'll talk about in a moment, are not affecting these phonons quite so much. And then the other one is that some of the zone boundaries, you actually see a little bit of sharpening. And so, yeah, it's a rather complicated thing, and the structure that occurs is fairly complicated. So this is picture. We also have some first principle calculations of the phonon dispersion curves. These had to include some disorder and unfolding because the zirconium and uraniums are randomly in a random solution to begin with, and so you have to include that disorder, otherwise you get unstable phonons. But the energies agree pretty well, and the energies are not that strongly affected by the irradiation, but the lifetimes are in certain places. And so you see down here on where the lifetimes are plotted, some of the lifetimes along in the middle of the zone, you see these kind of jump, a few of them where it kind of jumps up. And but it's generally pretty complicated because some of them actually go the other way, particularly at the zone edges. And you can also look at group velocities, and basically from looking at the dispersion, they're not changing much. It's just basically to within error, they're basically the same group velocities. But the lifetimes get more spread out with irradiation. So yeah, some of them get a lot shorter. And the bigger effects, so the top one is just basically all the lifetimes. It's not shown what's what there, and it's plotted versus 1 over energy squared in a log plot to give you an idea. That's sort of regular scattering or phonon scattering behavior, but it has all these other kinds of contributions, and the spread grows with irradiation. So there's a suppression of some, but this also occurs. The bigger effects are in the basal plane, less so in along the c-axis, and that turns out to be consistent with what we see in the thermal conductivity, which I'll talk about in a minute. So what's actually happening with irradiation? Well, is a lot. It's kind of a messy problem. So in the pristine sample, it looks fairly uniform, but when you irradiate it, you get these precipitates that form. These are something like 4 nanometers thick by 20 or so. So these are of course going to contribute to scattering. There's also small amounts of second phases that appear. You see these kind of faint peaks. So there's a little bit of alpha uranium, a little bit of alpha zirconium, and so extra phases get mixed in there. They're sort of a minority phase, but they are there. And we do actually see, when we do the fits to the phonons, we see little extra features in there that we have to fit and just sort of identify. Especially so the alpha zirconium is actually also hexagonal, so they kind of sit right under it. But yeah, so it's a complicated problem. But yeah, X-rays allow us to see these things. Yeah, so this is just. Yeah, so these are the actual size of the platelets, 24 nanometers by about 4.6. And so the middle of the zone, these kind of corresponds to wavelengths that are around those length scales. So that part kind of makes sense. The zone boundaries, we think that there's probably, as you start to form these precipitates, you're also cleaning out some of the short range disorder that may be affecting some of these very short wavelength phonons. And of course, the long wavelength phonons are maybe not seeing it just because they're much longer than the size of these things. So yeah, that's that. We also did some thermal conductivity measurements, and I won't get into this too much here, but the main effect is that we see with irradiation, yeah, there's generally a decrease in the thermal conductivity, but the decrease is largest in the basal plane, where we see the biggest drop in phonon lifetimes. But it also decreases along the z-axis, and a general effect is that the material becomes a lot more isotropic. Yeah, so these are kinds of things we can see. It's a complicated problem, but we can do that. So yeah, let's see. I got plenty of time. Ahmed asked me to say something about what could you do with the beam, and so I just thought about some speculative ideas. So if you have a 1 micron beam, it's nicely defined. I think you can start to look at parts in a material, look at phonon lifetimes in small regions where there's maybe strain gradients near defects or inclusions or boundaries and all that. But I was thinking about it, and I think maybe there's just like a nice way to sort of do this in a controlled way, and it also might actually be technically relevant. So I thought about, well, what would it look like to measure phonons near a crack tip, where you basically use the stress concentration near the crack tip to actually sort of modify the strain states, and it's an interesting problem, I think, to look at, because for one thing, yeah, it doesn't take much to create very large strains because you're using this concentration. It's also pretty well understood because it's a very important problem in mechanical properties. And also, yeah, knowing, so if a material's self-irradiating, the temperature can affect the tendency to crack, or how a crack grows. And so actually knowing how the thermal conductivity varies around a crack tip could be interesting. But it's also a place where you can just control things. You can create different strain states. You can create strain gradients. You can load regions with dislocations by moving the crack a little bit, depending upon the material, create a plastic zone. And so now if you're talking about having a 1 micron beam, you could go in there and actually measure phonon lifetimes in different regions with elastic strain gradients or height dislocation densities, things like that. So that's just something I'm just putting out there as a speculative thing to think about. And so the summary, so these were the first phonon dispersion in line with measurements in freestanding irradiated crystals. This is because this is just basically difficult to do anyways. And so, yeah, it hasn't been done in freestanding crystals. The phonon dispersion in pristine and irradiated UZR 2.6 are similar, but the line widths vary in complex ways. And the STM gives you some idea of why these things are happening. Although I think more modeling is needed. We have some modeling, but it's really difficult to explain everything. Yeah, and the observed phonon properties are consistent with the measured thermal conductivity. I didn't talk too much about it, but the electric thermal conductivity not really that affected by the irradiation. So we think that the changes are mostly due to the phonons, but there's a mix there, which makes it complicated here. And so I think that, yeah, such measurements are needed to understand these complicated relationships and these materials that are getting irradiated in a reactor or while being stored. And this is affecting temperature, safety, efficiency, and all that. So yeah, that's basically all I have.
Thank you, Michael. think you're gonna put us back on schedule, which is a good thing. Any question for Marco, since we have a few minutes? Okay,
Maybe I have a quick question. This is Olivier.
yeah, go ahead.
Hey, Mike, nice talk. Thanks. Yeah, this seemed like really tough experiments, so it's pretty impressive you're able to do that. In samples of you know, maybe non-irradiated are a little bit easier. What's your general experience with the kinds of line weights you can confidently assess on ARICS?
Oh, yeah, that's kind of good question. Yeah, we have, let's see, that's one of my view graphs. Yeah, kind of yeah, I mean, you can maybe, yeah, maybe you can get maybe 0.2 millivolts or something. You start to get down below that, it's not really meaningful. I think 0.25, 0.3. This is kind of I mean, it really depends upon the quality of your data. But yeah, somewhere, yeah, so you get this 1 point, you can go below 1.5 millivolts, but it starts to get very difficult very quickly.
Okay, thanks.
Yeah, so in this kind of picture, like these kind of things down at the, you know, down around zero, that's kind of meaningless. It's just they're very low. I mean, we know they're sharp, but we don't know how sharp, below 0.25 millivolts or so, something like that.
Okay. Thank you, Michael. Our next speaker, Hu Miao from Oak Ridge, also National Lab. So Hu, please go ahead.
Can you hear me?
Yes.
Okay. I do presentation mode.
Yep.
Does it look right?
No, it's
Oh.
showing everything. So because I think you have two screens. Yeah.
Yes. How about this?
Yes, now it's better.
Okay, great.
Thank you.
Yeah. Thank you, Eamon. Thanks for the invitation. I'm Hu Miao from Oak Ridge National Lab. Today, I'm going to talk about a little bit about our resonant work done at 30ID. It's our understanding of a charge density wave in a cognate magnet iron germanium. So I'll start by a introduction of cognate metals. What might be the interesting physics, why people are interested in the community. And then I'll give a quick review of a cognate superconductor. And then I'll move to the main topic of this talk. And then finally, I'll give a little bit the outlook about the, let's say, the future, a bright future of inelastic scattering. All right. So cognate. So cognate has been known for a really, really long time in the community. And the focus has been a quantum spin liquid. So the cognate structure-wise, it's a corner-shared triangle network. So you naturally have geometrically frustrated network. So if you have spin 1/2 and you have quite strong quantum fluctuation there, then you may end up in a quantum spin liquid state. But more recently, I think kind of motivated by the study of topological materials and simple band structure like graphene and twisted bilayer graphenes, then people start to think about the electronic structure of cognate systems. As you can see here, so if you're starting from a tight banding model and consider nearest hopping, then you're going to have three characteristic band structure. One is the flat band. The second one is the Van Hoff singularity near the endpoint, and the third one is the Dirac point as the key point. And you may ask, how do we use these band structures And here are some theoretical predictions. Let's say if you are able to tune your chemical potential to the Dirac point, and you are able to combine magnetism in your system, then you can generate a wild point. And if you further thin down your material to, let's say, few monolayers, then these wild points are going to open a gap, and then you're going to end up in a quantum anomalous Hall effect. The second interesting feature, of course, is the flat band. It's kind of a cheap way to generate a flat band, where because of the interference of the atoms, you're going to have a localized wave function, although your atomic wave function may delocalize. In this way, you can have flat banding here, and if you incorporate spin orbital coupling in your system and the ferromagnetism, then you can realize a fractionalized quantum anomalous Hall effect. So the third one is Van Hoff singularity. So if you familiar with those Tardensky system, then people may immediately guess, okay, if you have Van Hoff singularity, then you're going to end up in Tardensky wave, etc., etc. It has been known like for over 30 years or 40 years. So what's really interesting for this system is, again, go back to the quantum interference because of these three atoms in the unit cell. So if you check the wave function that connecting these nesting wave vectors, they're actually orthogonal to each other. What that means is if you only consider local Hubbard-U interactions, the nesting effect is going to be weak. So if you can generate any effect for a Kagami system, you should not really care about the local Hubbard-U interaction. So that makes this system kind of a really delocalized effect. So because of that, people studied the leading instabilities. So that's going to generate like a P wave spin or Tardensky wave, F wave superconductivity, and the Pomerantsev instability. So that's why even though we have the same Van Hoff singularity as other, say, honeycomb systems, in the Kagami system, it's really different and it can give rise a new physical effect. So one of the leading effects, actually, if you calculate the band structure and calculate the condensation energy, you find the leading instability is indeed a loop current, which has been initially proposed, first proposed by Holden to realize a quantum anomalous Hall effect, and then kind of proposed for the cuprate to explain the pseudo gap phase. So here, because you're going to form those local loop currents, you're going to induce a lattice distortion, which you can identify by inelastic or by any X-ray or neutron scattering that you may interpret as the Tardensky wave. So after this prediction, people start searching if their material system can realize those interesting physics, in particular near the Van Hoff filling. One major breakthrough was made by Brandon Orris, who was working with Stephen Wilson, and now he moved to Oak Ridge as a staff scientist. So he found a new set of Kagami metals, potassium, rubidium, and cesium, vanadium-3, antimony-5. So these materials feature saddle points near the Fermi level, and it shows superconductivity at a low temperature and the Tardensky wave at high temperature. So our group immediately interested in these materials, and we carry out a comprehensive RPS and the inelastic scattering. And here, just to show you from the RPS point of view, you already see the saddle point and the opening of the CDW gap. And if you check the chain number of the band, then you realize it's indeed a Z2 topological superconductor. Of course, we're trying to understand the CDW in the system and trying to understand what drives the CW in this interesting material. But nonetheless, here's a summary of those systems, and the people do find all kinds of symmetry breaking. So because of the formation of CDW, you break the translational symmetry. And we also point out, based on our X-ray data, that because you form a 3D CDW 2x2x2 or 2x2x4, you can also break the rotational symmetry. This kind of confirmed by transport measurements. But from the STM point of view, the Princeton group also claim there's evidence of time reversal symmetry breaking, and working with the muon group, and they do find some evidence of a magnetic response in the system. And then later there are a Kerr effect and a Faraday effect that seems also point to a time reversal symmetry breaking appears at the same temperature of a charge density wave. Moreover, there are more STM study seems indicating there's additional translational symmetry breaking, but now it seems more like a surface effect. Nevertheless, if you go to really low temperature, you see CDW combined with superconductivity and possibly this loop current giving you a what people call the Roton periodicity wave. So that basically says those kind of a material really have a rich phase diagram, rich symmetry breaking phase, and possibly new quantum state of matter. Then the question is, it's been 3 years after we studied this material. The question is, can we extend the physical picture, or if there are other materials that can host the similar physics? Later, I think there's an important discovery from Rice University, from Peng Cheng Dai's group. He found in a Kagami magnet, iron germanium, there might be some similar physics. So here shows the crystal structure of iron germanium at a very high temperature, around 400 K or something. So it's there's a paramagnetic to A-type AFM phase transition. So, and if you go a even lower temperature, and all of a sudden you have a CDW transition temperature, which is rarely seen in materials. But I'm sorry. And after the CDW transition, the neutron scattering group find that the local spin moment is enhanced. And by that time, they were puzzled and trying to, I think they were taking this as a key experimental signature to support a novel CDW mechanism, and they kind of are proposing a loop current picture. But all those scenarios, you still need other evidence. For instance, there's a STM group, again, from Princeton group, STM study from the Princeton group. They do find a CDW gap near the Fermi level. They also find a edge mode, seems indicating topology in the system. And again, from the APS group at Rice University, they studied the electronic structure and find evidence of Hopf singularity near the Fermi level, and kind of supporting the loop current scenario for these materials. For us, so why we're interested, there are two aspects. So we're interested in this material. First, there's a CDW deep in the magnetic phase, which is rare in the in condensed matter systems. Probably this is the only system that I know that you have a CDW that deep in a magnetic phase. So the natural question is, what drives the CDW in a magnetic phase? The second point that we are interested in is, of course, whether the system really another like a candidate to realize this Van Hopf singularity-driven loop current scenario. To resolve these puzzles, we first carried out a more like a DFT plus DMFT calculation. The first thing we need to understand the band structure, because on the DFT level, from previous studies, seems it's hard to understand. Then after you put the DFT plus DMFT calculation, then it looks like everything can be reasonably described within this framework. And you do see the saddle point pushed to the Fermi level. And this effect kind of related, partially related to the correlation, also partially related to the AFM ordering. Meaning, if you don't have AFM long-range order, the saddle point will not close to the Fermi level. So that's kind of an indication that AFM in the bottom line gonna push your saddle point to the Fermi level that may contribute to CDW. Then we start to explore the CDW structures. The first thing that we find kind of distinguished from this material to the vanadium Kagami metal or Kagami superconductor is that there are additional superlattice peak that kind of overlap the magnetic superlattice peaks. So that's kind of a miss in puncture or the neutron groups study. I think primarily because these vectors are overlapping. And then you probably need one little bit more characterization because X-ray is also sensitive to magnetic moments, especially for hard X-ray diffractions. So you need really confirm this peak is not coming from the magnetic peak. So we did a more systematic temperature dependence, trying to tracking the order parameter, and you see both this 002.5 peak and the in-plane CD2x2 CW peak has the same onset temperature that basically prove that it's indeed a charged superlattice peak associated with the charge density wave. So now the question would be, what's the lattice distortion associated with this 2x2x2 CDW in iron germanium carbon magnets? So one way you can kind of solve the structure, which is sort of difficult because the bigger superlattice. The other way, you just go back to DFT calculation and say, if you can relax your lattice structure and what might be the stable structure going to be. So we did a DFT plus U calculation, and you actually find that if you increase U, the lattice tend to unstable. Although, well, moving towards to a CDW phase. So kind of the main driving force is really the local magnetic moment. So if you have a larger local magnetic moment, looks like the system does not want to maintain the Kagami structure. And actually, if you starting from a 2x2x2 superstructure and relax your lattice structure, you end up really a 2x2x2 lattice distortion. And here shows the calculated ground state energy, where the 2x2x2 charge density wave actually has a lower energy, even at U equal to 0, even though you don't clearly see a phonon softening. And if you look into the atomic distortions associated with the 2x2x2 superstructure, you find majority of the atom in the Kagami lattice is actually out of plane. So that's kind of give us the indication that this may not be a nesting driven picture, because usually electron phonon coupling is stronger for transverse longitudinal phonons. So the lattice distortion are presumably more like in plane rather than out of plane. So that's kind of the picture for the vanadium Kagami metals. But here, a large number of atoms actually moving out of plane. So that may indicating the Fermi surface is not particularly important here. So then we need go back to the phonon spectral measurement and say, okay, if there's any phonon anomalies associated with the 2x2 wave vector and the 1x1x2 wave vectors. So the top one shows our elastic scattering data, dynamic structure factor collected at 30 ID. The bottom one is really a DFT calculation of a dynamic structure factor. The overall agreement kind of quite good. So, but if you look more carefully, then you find that near the what do we call half L peak, you do have a quite a large phonon anomaly. Well, if you go to the endpoint that corresponding to the 2x2x2 CW or connecting the nesting wave vector, there are really no phonon anomaly associated with that. So here show a couple of experimental raw data, and you already observe that the phonon kind of go softening as you go higher temperature. So the band renormalization, so this panel really compare the band temperature dependent phonon band renormalization as a function of temperature. For the endpoint, you really see no change. But if you go to the A point or the half L peak, you see like about 14% phonon renormalization from the magnetic transition temperature to the CDW transition temperature. In the same time, you can monitor the phonon line width, and again, the endpoint really show no broadening effect within our resolving power. But if you check the line width of the half L peak phonon, then you do see a pronounced enhancement of phonon line width. And once you enter the CDW phase, kind of the width get narrower again. So that sort of motivated us to propose a mechanism different from a traditional Van Hoff singularity-driven CDW, because first of all, because the vector does not match, and also because the phonon anomaly mainly occurs at the half L peak, 0 half L peak. So that kind of indication that the phonon and the magnetic kind of interacting with each other and giving rise to the phonon anomaly as well as the CDW. Before we move on to a detailed theoretical calculation, I want to make another comment about the magna-phonon coupling versus electron-phonon coupling. The main reason that it kind of another reason, I should say, that motivated us to exclude the nesting picture is really a comparison of two similar materials. One is iron germanium and one is iron tin. Both of them have A-type AFM. And if you check the band structure, they are remarkably similar. So they do have the same Van Hoff singularity near the endpoint, but still one has a CW, one doesn't. So that kind of indication that nesting doesn't really work for the iron germanium. So motivated by these observations, we start to calculate the phonon self-energy effect. Here shows the calculated imaginary part, real part, and dynamic structure factor. And from these calculations, the dashed line is corresponding to a magnon excitation, and the solid line corresponding to a bare phonon excitation. And if you see, and you can see here that by considering the magna-phonon coupling, you already see the phonon broadening and hardening effects that's qualitatively consistent with experiment. But I have to emphasize, this is really a very simplified model, does not consider the more complicated magnetic structure and phonon structure. So to us, a qualitative agreement is more like expected rather than a quantitative agreement. So then once we see the spin phonon coupling, and if you really go deep in the literature, it's actually not the first time it's been seen. In a spin pair system, people has been talking about this for decades. And here just to show a experimental paper back in 1998, where people have seen a spin phonon coupling effect in this spin pairs system. And similar to our observation that instead of a phonon softening effect, they actually observe a quite strong phonon hardening effect that is sort of consistent with our observations. But whether there's a more fundamental relation between these similarities, that's probably need further theoretical studies. All right. So before close out my talk, I want to comment about, generally from our perspective, the phonon, why phonon is important, why this inelastic actual scattering technique become important for condensed matter community. So historically, there are actually two main streams for the quantum research. One is spontaneous symmetry breaking, that's within the Landau paradigm, where you can have superconductivity, density wave, all kind of spontaneous symmetry breaking phases. The other one is sort of a parallel, is a topological excitations or topological quantum states that doesn't fit into the Landau paradigm. Then with our understanding of the topology and the symmetry breaking orders, people start asking question, can we combine these two together? So the case I just showed you before is sort of within this spirit, and we're trying to combine symmetry breaking orders and the topological property effect. And actually, there are already some theoretical predictions, including topological superconductivity, fractional quantum anomalous Hall effect, chiral CDW. But those new quantum states also pose questions that how do we characterize those quantum states of matter? And if you look at the energy scales, and we see for charge excitations, for example, the band structure, plasmons, and you actually covered the EV to like 100 MeV energy scale. But most of the time, we're interested to MeV energy scale, talk about all kinds of gaps. For spin excitations, similarly, we cover from 100 MeV to even MeV scale or sub MeV scale, depending on the spin excitations or spin textures. And for more like entangled fractional quasi-particles, so like orbitons, spinons, Majorana fermions, or gauge flux, the kind of, in particular for those spinon, Majorana fermion, the gauge flux that arguably can be used for quantum computation, is really like MeV energy scales. And then the question always be, how do we observe them? Many of them are delocalized. How do we probe those effects? Interestingly, because the lattice, all the excitations are based on a lattice, so you always need, so all those quasi-particles are going to interact with the phonon. So if you study carefully these quasi-particle interactions, and all this information should be encoded in the phonon dynamical structure factor, and you should be able to study them using inelastic X-ray scattering. And with that, I would conclude my talk. We kind of believe the spin phonon coupling plays an important role for the charge density wave phase in the cosmic magnets. And we believe the phonon dynamic structure factor are going to be key to uncover intertwined or even entangled quantum states. And I think I'm going to stop here and happy to take your questions. Thank you.
Thank you. Thank you. Nice talk. Any question? We have 2 minutes.
I have a quick question to, have you considered pressure as a variable instead of temperature to tune these properties?
You're talking about in general?
Iron germanium.
Iron germanium. Yes, we're thinking. We actually start from a transport under pressure. One difficulty is the CDW signature in transport kind of weak. So you see in Peng Cheng's paper, it's already you need to do derivative to see the effect. Now we're trying really hard to see if there's a signature of CDW or tuning the CDW with the pressure. If we can see signature, then we're going to study the phonon dynamics.
Thank you.
Any other question? If not, thank you. We have one change to the schedule actually. So Minda is going to present now, and Chen Li will move to the after him, basically. Okay, Minda, please go ahead.
Thank you. And also thank you everyone for the invitation. Let me try to share my screen. Can you see my screen? Amen.
Yes. That's
Okay,
good. Thank
great.
you.
Yeah, thank you. And sorry for the last minute schedule change. And today, I'm really happy to introduce everyone to two things. One is our recent experiment work at APS on the magnetic field induced this phonon change. And the second one, which I hope it can be used for the general inelastic community, is about a predictor. You can input the crystal structure like a CIF file and get to output from full phonon prediction band structure in one click. So the general idea, we really like a phonon. It's because it's really fit in this global energy, this workflow. So this is from the US energy workflow. No matter what kind of the energy source they come from, even a very clean energy, and the 2/3 of all the generated energy will end up at waste heat. And electronically, it's largely limited by the Weidmann-Franz law. When you carry heat, then the electrons also have to carry the useful electricity. So that's why the phonon, which as a major heat carrier, especially in semiconductors and insulators, will be the one main reason to lead to the so large waste heat. And then for today's presentation, first the experimental work, we picked up this one, the so-called topological nodal line semi-metal, this cobalt manganese gallium. So that material is pretty interesting for a few reasons. The first is a ferromagnet with extremely high above room temperature, QV temperature, and it has pretty much many wire nodes, just like wire thin metal. That's not the only thing. Imagine if you can link all these wire nodes with another kind of infinite nodes, it becomes a nodal line. So it contains all these kind of the different degree of freedom altogether. So that's why in the past few years, people have been confirmed this material have all kinds of these different types of the nodal lines and this even the wire nodes, and it also with the magnetism, the interplay becomes one interesting to answer. So besides some fundamental reasons, this material is also be interesting from this energy harvesting perspective. The one is it has a very large this Nernst effect. So people have been measuring this, if you have a longitudinal, like X direction, heat current, what are the voltage response and solely coming from this intrinsic barrier curvature of the topological nodes. Somehow this material is also probably one of the largest material, even with the famous larger than the iron and this PT, this multi-layer material. And in addition to that, we want to study why those topological features can have any signature on phonon. And based on the prediction we'll introduce shortly. And the idea is that the inelastic X-ray scattering has not been traditionally an approach to study the field response. But thanks to this very brilliant design of our beamline scientists, and we can finally be able to measure how this phonon dispersion changes as a function of magnetic field. In order to try to link to some unusual this phonon feature, so experimentally, the key thing is we want to find out two different configuration. One is this Q vector is proportional to B when they are parallel to each other. The other is that more conventional when they are perpendicular to each other, and see how that phonons can change from there. So, and in addition to that, because these materials have the different topological nodal lines and nodal rings, so the measurement has been also taken in the different sections, and some will have the cut along certain like a nodal ring along the line direction, like what we have here. And in some other measurements, it's like no crossing to the nodal lines. So we're still an early stage to analyze the data. The key idea, no matter what we choose, this Q and B, the difference is that this material has a very high symmetry. It's a cubic crystal. But for some exotic phonon feature, we also want to measure how it changes when you flip the polarity of this magnetic field, like the positive polarity or to this negative polarity. And because of this whole crystal symmetry, and it actually does not quite having this response for any asymmetric this field-induced phonon dispersion change. But if you really look at how the certain branches of the optical phonons changes as a function of this Q dot B, it actually developed a level of asymmetry. For example, along certain directions, they actually flip the sign, which means that one type becomes higher, one is lower, or at the certain other directions, and it also becomes a higher energy. So some direction it can be harder, in some other direction it can be lower. And the other thing is that there are very different splitting. It also happens along certain Q points. It almost have very little effect on this field-induced phonon energy change, but along some other directions, the change can be really large, like about 1.5 milli-electron volt. So what we were trying to do is actually giving pretty good agreement, especially we need a fitting parameter here, is to link all this to the possible phonon chiral anomaly. So chiral anomaly just means this fundamental is CP, this symmetry breaking. And in this particular case, when you have some kind of phonon and external magnetic field, when they align to each other, and it had been predicted almost 6 years ago by the theory group in Sherbrooke, mentioned that this kind of asymmetric, this phonon change, get an idea how this will shift as a function. It's actually, imagine if you have some kind of optical phonon, and then if you have the positive polarity, they may have some this hybridization between the phonon and the so-called this called pseudo-scalar this boson mode, and it really doesn't change too much. Or but if you have the switching the polarity, then the gap becomes open. So that is kind of what qualitatively similar to what we see before. If you have some kind of merging of the phonon frequency, or you have some kind of the deviation, and when you increase this field, and when you above that phonon frequencies. So that's is our ongoing work, but we believe that adding magnetic field can be really exciting for the future inelastic experiments. So with limited time, I will move to the second part on how to predict full phonon dispersion and with machine learning. Particularly, just input this your favorite structure file here. So in the past few years, there are so many works related to the so-called graph neural network. This is a type of the work to represent molecules or materials. The easiest understanding, you can put this one atom as the node in the graph and put all this interatomic bonding or the relations as the edges of the graphs. And people have been using that to study many molecular systems, drug design, and also solid state systems. And particular one frontier is to use symmetry to augment that kind of the graph neural network. Imagine if you shift the crystal, rotate it, it's still the same crystal, then that symmetry augmentation should be able to tell information like that. But there is still one key limitation, because the graph neural network deals with only input layer as the first step. If you look at all the drawings here, the first step of the machine learning model, and all the rest are still this conventional machine learning model. That means it forwards one limitation about the length of the output part. Imagine we still have all these atoms as nodes in this graph and all the interatomic bondings as edges of that graph. And then the typical graph neural network will try to do some convolution between all these graph edge features and then aggregate them. But the final this prediction is a fixed length vector or some quantity. But imagine there are many other material properties. They really don't have a fixed length. It can be vary material by material, and phonon is actually one of them. If you have m atoms per unit cell, there are 3m branches of the phonons. How to endow this level of flexibility of that neural network? That's how we propose to add a virtual node. Other than representing the real atoms, the virtual node is more like a storage, this register stack, and you can add as many these virtual nodes as possible. Virtual nodes can also do convolution to each other, so that's why it's an orange bidirectional line. And the key thing why it's not interfering the real virtual node, the original graph neural network training, is you only have unilateral this direction from real node to virtual node. You can pass information, but not the other way. And then the good thing is that depending on how many virtual nodes you add, you can really have a variable length of the features of the output. So then we propose 3 types of virtual nodes, try to predict the phonon, and two of them are for gamma phonon, and one of them are for this full band structure. The first and the most naive one, if we want 3m phonon bands, then we just add this 3m virtual nodes. The virtual nodes also have this virtual features that's like a real nodes. But imagine after all these real nodes inputting the machine learning graph neural network training, and they put all these 3m values into that one, sorting them from the lowest to highest, just directly predict those 3m as the eigenvalues of this zone center gamma phonons. And then these are the typical results. The left, this is 4 columns, and are just from a simpler but high quality database. The rightmost column is from another database containing complex material, but the lower quality for the calculation. Throughout all the presentation, all the black colors represent the ground truth from the ab initio calculation. As you can see, if we divide by 3 error tertile, the top row are the top performed this material, and the worst is this bottom row. We can see in the simple material, the agreement in the top 1/3 is pretty good. But if you have a complex material, even the top 1/3 is not so good. And this can also be seen from this error distribution from the simple solid, which will really mean that the number of atoms is smaller than 24 actually, and all the loss function is leaning toward the lower side. But for complex solid, it's become really high. The same happens at the average phonon frequency. If the predicted average phonon frequency lies along the diagonal line with the ground truth, that means the higher quality. For simple solid, it generally aligns along this diagonal line, indicating the good performance, but it's really not good for this complex solid. So that means that this direct, naive way to add virtual nodes need a remedy here. That's why we have been asking, is this eigenvalue the most intrinsic thing for the phonon? It's actually not. The more intrinsic and more fundamental quantity is the dynamical matrix. So we propose the second version of that virtual nodes. Instead of directly adding 3m, this virtual nodes, for each atom, we generate this virtual crystal. It has like a m nodes. And then because you have m atoms, eventually it generates like m by m, this virtual nodes. Each virtual node here is also not a number, but itself is a 3 by 3 matrix. That means you have a 3m by 3m matrix there. So that is some matrix, and you can fill in the numbers through this machine learning training and by filling in based on these graph structures. And because this matrix share exactly the same structure like the real dynamical matrix, by solving the eigenvalue problem and take a square root, and then maybe that's another alternative way to learn this phonon, gamma phonon frequencies. The difference is that comparing to the real dynamical matrix, when people doing is to compute like interatomic force constants, and here it's not computing any interatomic force constants, but it's from this machine learning training from other materials that may contain the same this element. So that has much lower computational cost. So here you can see the general performance also plotted in a 3-arrow tertile. 3 row just means top performed, medium, and the worst one. And as you can see, as usual, because there are many material containing certain like selenium and tellurium, the performance is okay. And even in a complex solid, and the performance becomes much better, which you can also see from this loss function distribution, and also with this average phonon frequency. We're still aware because there are many material containing rich in hydrogen, but has been lack in the training data. And for some material with very, very high phonon frequency, we see there's a pathway for further improvement. And then the question is that with this agreement for gamma phonon, this prediction, vibrational spectral, can we go one step further, try to get the full phonon band structure? So then the key ingredient, how we can input the correct Brilliant zone and correct k-space information into the graph neural network. The thing is, the graph neural network is a real space quantity, right? One atom is a real node, and the interatomic relation is this graph edges. There is really no space on the reciprocal space. To see this one possibility, how to get this momentum, finally, we came up with something that can use this crystal translation. Imagine this T0 is our original data crystal, and you can just build this virtual dynamical matrix just based on data crystal. But right now, to get to momentum, you can do the translation. Imagine from T0 translated to some like a nearest neighbor like a T2, then there's another unit cell. You can build another kind of this dynamical matrix from the neighborhood unit cell. And then it's possible to just sum over all that neighborhood and build this momentum. So if you have the dynamical matrix at the neighbor unit cell, as long as you can multiply by this 2 pi k times this translation vector and sum over all these neighbors, that gives one way to do this dynamical matrix. To clarify, this is very different from the real dynamical matrix, because the real dynamical matrix is the summation of all the unit cells. But imagine in this case, it's only sum over like nearest neighbors, like a magic this Rubik cubes, only like a 27 nearest neighbor, including the center one itself. The reason is that when people say the node is the graph node, that's true, but the interatomic bonding is the graph edges. It's not quite true because the graph, to make it a valid graph, to be able to pass through layer by layer to do the training, it only requires all the graphs to be connected. That means as long as all these graphs are connected, it will be a valid graph to perform machine learning. So that's why the value here, even though it shares the same dimension and the structure as the real dynamical matrix, because it comes from a different origin, summing over nearest neighbor, and instead of computing interatomic force, but instead doing the this machine learning training, so it's not a real dynamical matrix, so we term as the virtual dynamical matrix. Here are also the typical performance. And also the 3 rows are the 3 aerial tertile in a simple this database, and also this complex this database. And then you can imagine that you can really rapidly to try to calculate the full phonon band structure and in your personal computer. And that's not the only advantage here. The other thing, and these are just some more results to compute from the simple solid and also some this larger solid. We also learned some this advantage to be computing like oxide or this some limitation when you have very strong electrostatic effect like a hydrogen or lithium, then the performance becomes much worse. And so some very complex solid, you can see it can also try to learn also the phonon band structure. Can see in the top to perform the category, even have complex solid, and but with oxide, the agreement it should be okay. And then another advantage is how to encode alloys, solid this alloy. So here are the typical results, like the ground truth from this ab initio calculation plus virtual crystal approximation, and this predicted value also from here at different compositions, and also some metal alloys or even some high entropy alloys can also be computed. The good thing is that using this machine learning based this encoding, even predicting alloy, it does not add any computational cost. The reason is that for the virtual crystal approximation, it is some kind of this weighted average between this mass. If you have 2 atoms A and B occupying the same site, the virtual crystal, the mass is the average, and the virtual crystal's potential is also average potential. In the current way to do this encoding, it's each atom is like a long vector, and if you have this different component turning on, and then you naturally represent that type, the 2 equations into 1. If you change which component they are, you're like changing different types of atoms, and then you certainly can change the mass ratio by endowing the number there, and then by doing that, even you can try to calculate a phonon dispersion for this kind of the high entropy alloy with 5 different elements occupying the same site. You can just turn on 5 components simultaneously, and then without like a conventional ab initio method, you need to do this Brilliant zoom, this unfolding, and then to get this final results, you can directly get this dispersions in 1 step. And to get an idea what are the related computational costs compared to ab initio approach, the ab initio like a frozen phonon or this DFPT approach goes to scale like m to the 4th to 5th order and the number of this primitive unit cell. So in this current approach, it roughly goes to the m to the 2nd order or less than m to the 2.5 order. That means that if you have this atoms per like 100 atoms per unit cell, and it can reduce the cost by roughly like 1 million times. Or and we tried even you have like 1,000 atoms per unit cell, you can easily load them and without having to consume to a supercomputer. So that's how we also build the gamma phonon database for all these materials in material project. And we just build another database for zeolite and for the full phonon band structure for this energy harvesting and absorption these applications. And I think with that, the first part we don't have any preprint yet. It's our preliminary analysis. The second part we have the preprint, and we'll be happy to discussing further and happy to answer any questions. Thank you very much.
Thank you, Minda. Any question?
I have a question.
Yeah.
Amina, very nice talk. I have a question about your first part. So you said the material has a very high magnetic transition temperature. So I assume the magnetic interaction energy scale is going to be very, very high, or the local moment is going to be very large. So, and 1 Tesla or 2 Tesla is a fairly small energy scale. So why do you expect there are going to be major changes in the phonon structures?
Thank you, Hu. That's a great question. So that's due to this topological nodes from what we can understand, because we have other directions. When there's other brilliant zone direction, which you don't have the coupling between phonon and this nodal line direction, then the phonon is almost negligible. It's a really good question.
I have one question, Ayman, can I?
Go ahead, Arjun.
Thank you, Mingda. Nice talk. You mentioned something like starting from a .cis file and going into phonon dispersion curves. Is that currently available, or is this something in the future?
It's available. So we have shared in GitHub, and we try to make it as user-friendly as possible. If you like to give a shot, and we're happy to work with you to set it up. And it has already been set up in like Oak Ridge, some vibrational beamline, and we're hoping this can also help beamline user as well.
Thank you.
Great, thank you. Any other question? Okay. Thank you. Ahmed, you want to take over?
Thank you.
Yeah, sure. So next, we are going to continue with Chan Le from University of California, Riverside. And he's going to talk about monolayer-like lattice dynamics in bulk WSE2 structure. Please go ahead.
Okay. Thank you, Ahmed, for the introduction. Thank you, Ayman, for inviting me for the workshop. So my topic of the talk is slightly changed. I will talk a little bit more in terms of phonon chirality measurement we did recently. It's still some preliminary data, but I hope it's actually it's quite interesting. So before I start, I would like to talk a little bit about, well, acknowledge all the students who contribute to the work. Without them, what I'm showing here won't be possible. And in particular, Qing'an, as you can see, he's standing at sector 30 here in this photo. And Songri, he helped a lot with the high pressure experiment we were working on. And Qian did a big part of the simulation. Yaoken is also doing that. And also Bingwei, who was visiting from Jiamen Hong's group for with us for a little over a year. And he worked on some of the palladium selenide work we're going to talk about later on. So again, I would like to acknowledge all the beamline people, Ayman, Ahmed, and also Thomas, who helped us with the X-ray circular polarization generation. I'm going to talk more in detail later on. So this is what we do in our group. So we work a lot in terms of on lattice dynamics and spin dynamics and thermal transport related problems and spin phonon interactions, magnetic phonon interactions. And I actually highlighted some of the part that benefit greatly from inelastic scattering. So in particular, lattice thermal transport. And we also got time to look at phonon in some of the low dimension materials, such as 1 dimension nanothread, 2D van der Waals type of material systems, and even some quantum nanodots, but that's mostly for the neutron part. And we also are working on high pressure spin and lattice dynamics. And in particular, we are interested in thermal transport under pressure, and this couples well with our time domain environment in terms of phonon thermal transport. But today I'm going to focus mostly on talking about some van der Waals materials and how the lattice dynamics works for them. And also I want to spend a little time going through what we've done with phonon chirality and how we use the polarized X-ray for inelastic scattering. So to start with, the van der Waals material we are working on are primarily transition metal dichalcogenides. As you can imagine, those materials has pretty broad engineering applications, but also very interesting physical properties. And some of the properties actually inspired our work. One of the property involved is anisotropic thermal conductivity. You might think this is kind of intuitive because between layers, van der Waals type materials are weakly coupled. The thermal transport is expected to be quite small, but we actually see some large anisotropy within each of the planes too. So which is one of our motivation for some of our work. And also we are interested in looking at the outplane flexor modes. Those are unique to van der Waals interactions, and they have their own special dispersion relationship, and we want to see is that provides us approach to understand the van der Waals interactions. And in addition, does that contribute or changes thermal transport in such important material systems? Here, I want to go over actually quickly and how we did some of the high pressure inelastic neutrons X-ray scattering work. It turned out to be much trickier than we initially imagined for various reasons. Firstly, the material is actually pretty difficult to work with. As you can imagine, van der Waals type of materials are layered. They are banded pretty weakly. So any machining or even tweaking of the sample can destroy the crystallinity of the materials. And we find by working through the material system that even focused ion beam doesn't make good sample. So we have to cut it mechanically and load the cell and make sure that it's in the right orientation. And hopefully after gas loading, it still stay in the right orientation, allow us to assess the Q point we are interested in. And it turned out it's extremely difficult. We tried over 100 loading for this palladium selenide system we're actually working on. I'm showing here. And eventually we find some tricks, but it's also the combination of luck in loading that make it possible. So basically what we need to do is we have to cut the van der Waals materials to very small pieces using microknife. And we have to cut in certain batches so that allow us this small crystal to be loaded carefully in the diamond envelope cell. And then we hope during gas loading, the crystal won't rotate and then mess our orientation. And a lot of times we can have good orientation, but the crystallinity is so much degraded, has been so much degraded after loading. So we have to restart from scratch and load again and again until we find one working sample. So let's talk a little bit about what we done in terms of this phonon dispersion measurement under ambient conditions. So this is our measurement on Hurix, showing the phonon dispersion along several high symmetry directions for palladium selenide. And as you can see, it agrees pretty well with the density functional theory calculation. And it turns out the van der Waals interaction incorporated into those calculations doesn't matter much in terms of the bulk phonon dispersion. And we can reproduce reasonably quality. And one thing to notice is that there is actually a big difference between the phonon along gamma X direction and gamma Y direction. And this gamma Y direction turned out to be the direction that has very different thermal transport along X direction. So initially we thought, oh, maybe the flexor mode and the dispersion of the flexor mode have significant contribution to the thermal transport. But turns out it's not the case. And we'll show more results later on. We'll also try to extract the phonon line width out of those measurements. As you can see, the line width is very narrow. So I'm sure we cannot completely get rid of the instrument line width contribution. So there must be a lot of leftover and some of the fluctuation probably from counting statistics. But if we plot all those phonon line widths we extracted versus our first principle calculation, you can see, even though we are still missing some line width contribution, but the general agreement is actually not too horrible. We are able to get an overall trend which is consistent with what our prediction was. And of course, the phonon lifetime is still pretty long for those acoustic and even the flexor modes, but we kind of get the overall trend right in this case. And turns out in this material system, we later find out that if we perform careful calculation, it is one of the widest crossing that contributes mostly to the different thermal transport along A-axis and B-axis. As you can see in the middle panel, there is a large discrepancy between the phonon group velocities in the range of 5 to 10 MeV. And those energies are still pretty low and contribute significantly to the thermal transport. And because of such a wide crossing, also is shown on the right-hand side, we have a big suppression of the thermal transport along gamma X direction, which actually, because of this wide crossing, the transferred acoustic phonon mode group velocity almost come to a zero. And this is not compensated by the optical branches because their group velocity are actually similar to what we're seeing in the other direction. So we actually thought, oh, this is interesting. We want to look into more about this flexor mode. And this is what we did. We put the sample in diamond cell. We try to reproduce the thermal, the phonon dispersion measurement under high pressure. And first we have to validate that the loading is good. And we also have to be able to recreate the phase transformation, which we know is around a little bit over 5 gigapascal. But you can see here, the crystal actually behaved quite well through the phase transition. And we were able to extract, this was also done with Hurwicz in situ, and we were able to extract the lattice parameter nicely. And we follow through this phase transformation and from orthorhombic to a tetragonal phase that is about 5 GPa. So we think, oh, it's great. And with the sample loaded, we were able to actually map out the phonon dispersion, mostly on the acoustic phonons, both for longitudinal and transverse and the flexor mode for all those three branches. And the results are actually quite surprising. For longitudinal and the transverse modes, they are working as expected. So with the increase of pressure, we see a stiffening of the phonon modes. And up until phase transition, we see a sharp drop of the phonon dispersion and there's phonon energy, related phonon energy. And that is expected based on our atomistic calculation. And the agreement is pretty well. And for the flexor mode, it's different. It's initially the phonon stiffens, but there's also a dramatic change of the shape of the phonon dispersion. We start with something that is more parabolic-like, then it's gradually got more linear over the increase of pressure. And even before phase transition, this flexor mode become almost linear. And upon phase transition, it stays linear for the low energy range, and it stiffens slightly, but does not change very much. And we actually played with multiple van der Waals interactions for the calculation, and the result is, oh, they don't really differ much across different models. And we spent a little more time looking at the flexor mode, and this is what we got. We can fit the phonon dispersion, low energy phonon dispersion part with the power loss, and by extracting the power exponent under different pressure, this is what we found. We found that initially, this is not really parabolic-like as what we would expect from a monolayer sample, but it's still pretty much curved compared with the linear phonon dispersion you would expect from a covalent bonding materials. But with the increase of pressure, it becomes more and more covalent-like. And eventually, after phase transformation, beyond 5 GPa, the phonon become pretty much linear. We were able to also extract some of the elastic constant. As you can see, there's this quick stiffening and then the weakening upon phase transformation. We can even figure out some of the bending force constant for the layers, and which actually weakens with increased pressure. So there's actually a lot of information we are working on here. We look at transition from a van der Waals bounded bonding state between layers upon compression and a continuous evolution towards more linear-like interactions and in covalent bonding, and upon phase transition, it's become completely covalent type of crystal. So we also performed some type of temperature-dependent measurement, and this was actually done try to understand more further on how we should model the van der Waals interactions and related phonon dynamics. It turns out, upon working on tungsten selenide further, we realized that if we do perform the calculation with experimental measure lattice constant, both bulk and monolayer calculation agrees really well with our inelastic accurate scattering measurement. As you can see, we mapped out very extensively not only the acoustical phonon but also optical phonon. For bulk, we have a unit cell that contains 2 layers, so that's where this kind of folded phonon dispersion comes into. But for monolayer, we have a very simple phonon dispersion in comparison. Fortunately for X-ray measurement, we are only seeing one set of those phonon dispersion in each Boolean zone. So there is actually no confusion coming from having multiple branches or on top of each other, as you would expect for a box system. Okay, but the problem is we cannot relax the lattices. Whenever we relax it, the phonon dynamics go so differently, and we see up to 15 to 20% energy difference in phonons if we relax the lattice to its ground state. So we actually performed additional temperature-dependent measurement, and this is what our results show here. For most of the other phonon modes, I'm only showing transverse acoustic phonon as an example. The phonon stiffens with decrease of temperature, as showing with the blue dot here. And that can also be seen on some other phonon branches. But most interesting is for the ZA phonon, which is a flexure mode. Here I'm showing some of the phonon spectrum, and you can clearly see at lower temperatures, for example, along gamma K direction, the phonon actually softens significantly at lower temperature. This is not what we would expect from a typical mature system, so there are definitely a lot of unharmonicity involved. And we performed a further calculation, try to extract the group parameter using both the temperature-dependent phonon dispersion, but also the sum expansion information. So this is what we found. We were actually able to find the group parameter to be pretty small for most of the volume in the reciprocal space, but near gamma point, this flexor mode has a very large negative group parameter that is inconsistent with what we would expect by looking at the Hurwitz experiments. And it turns out if we perform a bulk density functional theory calculation, it doesn't matter how we perform it, what type of potential we're using or what type of van der Waals interaction correction we apply, it more or less reproduce majority of the group parameter, but fail to tell us what happens near gamma point. So we do not expect to see those harmonic phonon softening at low temperature. But if we perform a monolayer calculation, and it's actually reproduced nicely. So this is actually our conclusion. We figured that if you look at tungsten selenide in particular, the phonon calculation works a lot of time much better, in particular for its harmonicity, actually follows more or less what a quasi-harmonic model will predict for a monolayer system. And the inclusion of the van der Waals interaction between layers actually made it difficult to reproduce what happens with the flexor mode. So it turns out most of the van der Waals interactions were not tailored to realistically reproduce phonon dynamics in this type of material system. So there's still a lot unknowns going on here. Okay, so a quick summary on what we learned about the van der Waals materials. We know there are giant harmonicity or non-harmonicity in the flexor mode. This has been shown for both pressure and temperature dependent measurement. And we can definitely tune it with pressure and temperature. And sometimes we find that the monolayer material simulation actually produce lattice dynamics much better. And there are definitely a lot of open questions. One of them is, how does this nonlinear acoustic phonon affect thermal transport in terms of phonon-phonon interactions? We actually performed a lot of calculation in terms of scattering phase space, and we believe it does make a significant impact on thermal transport, but really depend on what particular system we're looking at. And so with that, I want to move on to the next topic I'm going to talk about, which is the phonon with angular momentum or chirality. And well, there are actually quite some talk today about phonon chirality, but we are understanding from different perspective. So in overall, lattice vibration in any structure can carry angular momentum. The problem is when they are eigenvectors. Turns out we can make phonon eigenvectors with angular momentum if we break either time reversal symmetry. This happens a lot with the magnetic systems. If you have a magnet, basically the time reversal symmetry is automatically broken, or if you have a spatial inversion symmetry. And if you break both, it's also possible to have a phonon angular momentum, but it's not guaranteed. The two can actually cancel out for certain material system. So this has been pretty extensively studied and investigated theoretically, especially in the last 10 years. So the question is, can we observe them? There has been some experimental observations through optical spectroscopy, but those are limited to gamma point, as you would expect. And sometimes those measurements are indirect and hard to actually trace down exactly what's going on and whether the anomaly observed is a result of phonon chirality itself. So, to work on that, we had to find one good material systems. Turns out the space group that allows angular momentum in phonons have to have broken inversion symmetry. There are not that many, so at least a few of them. So there are a few others, but not very many of them. And also, if we looked on the pure phonon side, it's impossible to actually break the symmetry significantly, even if the material is magnetic, because the magnetic moment is actually quite small. So we have to look through those space groups and try to find out which material system works best. And obviously, if it's 1D, it's actually easier to work with, but we're working with box systems, which means finding broken inversion symmetry is harder. One material we were able to find was actually tungsten carbide. This is a material system with reasonable scattering cross-section and with nice phonon energy to work with. In addition, we can get a hold of good quality single crystal. So this is our dispersion measurement using Hurwicks, and in comparison with the density functional theory calculation. As you can see, the agreement is pretty nice, and it agrees well with the literature calculation, and it also agrees distantly with our neutron scattering experiment for the density of states. But what's more interesting is shown on the right-hand side. If we calculate the phonon eigenvectors and use the phonon eigenvectors to calculate the angular momentum carried by the phonon mode, and this is what we see. As you can see, through most of the Brilliant Zone, there isn't much phonon angular momentum or phonon spins per se, but near K point, which is at the very edge of the Brilliant Zones, we see a purely right-hand and left-hand phonons. And those two phonons actually have different energies. So they are they're non-degenerate and with a small energy gap in between. So this provides us a good opportunity to probe the phonon there and see whether we should be able to see those phonon chirality through inelastic X-ray scattering. So before we show the data, I want to quickly actually go through the dynamic structure factor for one phonon scattering process with X-rays. So one important take-home message about the formalism we've been using so far is this was derived completely from the neutron perspective. And there isn't any consideration in terms of the polarization for X-rays. And as you can see, the dot product is a dot product between the phonon icon vectors and the Q vector of this, the change of this, the K vectors of scattered photon in this process. So there is actually a lot of questions going on. So for example, when we scatter one photon of a phonon, when the phonon contains angular momentum, is there a transfer of spin or angular momentum in that scattering process? Of if there's such transformation, so if there's such transfer, does this affect the overall dynamic structure factor we are seeing here? So turns out the answer is both yes and no. It depends. So this is actually our first experiment, and we thought, oh, we should be able to see some anomaly by scattering X-rays of those transverse acoustic and longitudinal acoustic phonons, as we shown previously from the calculation. But we didn't observe any disagreement from our calculation. Here we're showing the fitted experimental results in red line on top of this dashed calculated intensity. You see that the T and LA are supposed to have a very similar intensity at many breeding zones, and our calculation actually agrees almost perfectly. And we thought, oh, it's interesting, it's a non-result. But with further looking, what we realize is we are actually scattering, performing a scattering experiment in this in-plane geometry, which means our scattering plane here is in the basal plane of the hexagonal lattices for the tungsten carbide. What happens here is, in this case, both TA and LA angular momentum are going to be aligned perpendicular to the polarization of the X-rays, because the X-ray is horizontally polarized, and we have 90 degrees difference between the two. So maybe that's what's driving this non-result. It turns out that when we flip the crystal in a later experiment, and by the way, if you are doing scattering those two geometries with neutron, you should see no difference, simply because this doesn't change the phonon icon vector, and this doesn't change how the photons are going to be scattered off those periodicity of lattices in this material system. But we see a large discrepancy between the longitudinal intensity and the transverse intensity ratios between our experimental result and the simulation. You see the it's definitely difference from what we would expect. One thing to notice is we do see ZA mode, which is forbidden for this geometry, but we were able to triangulate this into a multiple scattering process, which is not part of our measurement here. And we have confirmed we do not see multiple scattering for transverse acoustic and non acoustic mode. Okay, so that's interesting, but this doesn't provide us enough information to understand what is going on. So what we end up doing is we think, oh, it might be a good idea to see how the phonon scatter with circularly polarized phonons. And this is what we end up trying to work with in X-ray scattering using X-ray polarizer. And this is a polarizer we use with the help of Thomas. And it actually works pretty nicely by having a diamond crystal and aligned almost to the Bragg condition, but off-tuned slightly. And at this scattering condition, well, at this transmission condition, the diamond crystal more or less work like a wave plate. So as you can imagine, if we change the angle of this wave plate, we should be able to tune this linear polarized X-ray incoming beam, and we can make a circular polarized either left hand or right hand, or we can actually rotate the polarization vector. So it turned out it's much harder than we expected. We suspect the difficulty is coming from working with the beam that has been through high energy resolution monochromator. And it's also possible that the narrow bandwidth of the beam, which in the MEV energy resolution make it difficult to work with. But after several trials, we were able to get it working reliably. As you can see here, this is our measurement actually of the beam using two detectors. One is placed horizontally off the beam, the other is placed vertically off the beam. We were able to reconstruct the linear component and the circular polarized component of the beam after the beam passing through this polarizer. So the dashed lines are our model, and the red lines are our measurement. You see that the agreement is pretty well. So here comes the result if we use this beam to look at our phonons. And here I'm showing 5 spectrons. This is going from 100% left-hand circular polarized to linear polarized and to right-hand circular polarized. And by the way, each of the spectrum actually takes a lot of counting statistics simply because the beam got so much weaker after the polarizer. But we definitely see a change of the intensity ratio. So that ratio change is actually almost a factor of 2 difference between polarized beam, circularly polarized beam, and the linearly polarized beam. And the middle line is similar to what we've done previously, but once we use a left-hand or right-hand circularly polarized beam, the intensity difference is very, very different. We are still trying to figure out what is going on, in particular, why the response is symmetric on both sides. We went through a handful of models, but so far none of them were able to tell us exactly what's going on, but we definitely see a non-zero result when we work with circular polarized beam. So here comes our conclusion. So well, the scattering formalism for the dynamic structure factor definitely works for linear polarized X-rays if we are looking at in-plane scattering geometry when we are working with chiral phonons. But once it's out of plane, once the intensity doesn't agree anymore. And we are able to use circular polarized X-ray and to see that there's anomalous scattering intensity between different polarizations of the phonons. And it's possible actually to do such inelastic scattering with polarized X-rays with very narrow bandwidth. So, but we actually open more questions than we solved, because now the questions are, okay, what is the right rule to calculate inelastic scattering intensity, and how does this angular momentum transfer between phonon and photons in this process, or what selection rules are there in this process? And if those 2 problems are answered, we should be able to use this as a probe to probe the chiral phonon dynamics, and maybe further to understand the questions of does those phonons have a special properties that can affect their thermal transport process. Okay, that's all I have today, and thank you.
Thank you, Chan. Since we passed time a little bit, maybe if you have any question, we can ask at the end of the discussion, and we can move on to next talk. And our speaker is Woo Kim, who is a visiting student from Pohang University from South Korea. And please go ahead, Huyan. Huyan, are you there? I see you, but okay, great, it's coming. We cannot hear you. I see that your microphone is on, but somehow I cannot hear it. I don't know if anyone else is hearing, or it's just my problem, or can you check your speaker?
Cannot hear him.
Yeah, we are not hearing you. I mean, I see your microphone is on actually.
Check your audio setup.
Right?
Yeah, okay. Now we can hear you.
Ah, really? Okay. Then is it okay? Okay. Okay then. Okay, let's start.
Yes, you are fine.
Hello, I'm Hyunwoo Kim. I'm a student at Post-APS Korea. I have been working in Sector 30 for a few months as a visiting student. And today I will talk about the origin of chirality in 1T titanium diselenide with the inelastic X-ray scattering data measured at Sector 30. This project is mainly driven by our group under the direction of Professor Bum-Jun Kim, BJ Kim, the students Hyunwoo Kim, me, and Kwang-rae Kim and Seung-Hyuk Ka mainly performed the experiment. And beamline staff at Sector 30, Aiman Said and Ahmed Alata support our measurements. Let's start from the chirality. An object is called chiral if it cannot be superimposed onto its mirror image. A representative example is our hand. A mirror image of right hand become left hand, and the left hand and the right hand cannot be superimposed. So it means that our hand is chiral. For crystal, the more strict definition of chirality is absence of inversion center or mirror glide plane or roto-inversion axis. So there are two examples how chiral symmetry can be broken in the crystal. First one is spin density wave. A spin density wave system is chiral when spin density wave can be expressed by product of three non-coplanar vectors. And the other example is charge density wave. It is known that in Kagoma material, potassium vanadium antimonide 135 and the transition metal dichalcogenide 1T tantalum disulfide have a chiral charge density wave. But it's a little tricky to think of chirality in charge density wave because charge density wave is a scalar quantity. So similar to the spin density wave case, we should consider three non-coplanar vectors. And chirality in multi-Q charge density wave materials can be realized by three propagational vectors. Our materials 1T titanium diselenide has also multi-Q charge density wave. It's known that it has a structural phase transition at 200 Kelvin, constructing 2x2x2 unit cell, and the atom moves along the summation of three phonon eigenvector at L points. Left figure shows this CDW displacement, and this I will keep talking about L points and M points. This means that high symmetric zone boundary points in a primitive cell. Right figure shows the first beryllium zone in reciprocal space. Here is L point and here is M point. So as you can see, L points have a L component. So this is the reason why that the displacement upper layer and lower layer have a opposite direction. So this displacement lower the symmetry from P3 bar M1 to P3 bar C1. The bar in the name of space group means that the existence of inversion symmetry. So these materials is regarded as achiral for a decade. So the displacement can be detected by measuring phonon. It is known that L phonons start to soften near critical temperature and it freezes at 200 Kelvin, which means that the energy goes to zero. Left figure is calculated phonon dispersion by adjusting one spring constant, which is done by Holtz and collaborators. From this dispersion, they could explain the thermal diffuse scattering pattern. So in the right figure, Frank Weber and collaborators observed the complete softening of L point phonon by inelastic X-ray scattering. When phonon freezing, the displacement is induced along the phonon eigenvector. So the original CDW is charge fluctuating L points. In the band structure, there is a hole pocket in a gamma point, and there is electron pocket in the L points. The charges at the gamma points and L points fluctuate, and this charge modulation is coupled with phonon at same Q points, L points. It generates structural phase transition. Recently, chirality beyond the known structure has been an issue in 1T titanium diselenide. STM data measured by Ishioka and collaborators inferred that the inversion symmetry is broken in this material.
they found superlative structure here, and they found that the tunneling current along the 3 different directions have a different modulation. This is the image, and this is line cut. And they did Fourier transform on this image. The result is figure C. And there is a certain direction in which the CDW peak increases. For here, it's counterclockwise. So this observation can be interpreted as due to chiral symmetry breaking at low temperature. So what's the reason why people could not find chirality for a long time? The answer is in the right figure. In the right figure, they measure 2 domains with domain walls between them. And in one domain, the CDW increases along the clockwise, and the other domain CDW increases along the counterclockwise. So because of the domain structure, macroscopically, it's just look like achiral. So let me introduce another experiment. Su Yang and collaborators first measure macroscopic chirality in 1D titanium dicylinder. They measure photocurrent depending on the polarization of the light. It's very interesting. In their research, they shine the circular polarized light while cooling the sample. For example, let's say that they shine the left circular polarization. And when the sample is cooled with left circular polarization, the photocurrent is also maximized at left circular polarization and minimized at right circular polarization. And the right figure shows the difference between maximum and the minimum. And there seems to be a phase transition at about 175 Kelvin, which is 25 Kelvin below non-critical temperature. So therefore, they claim that there is one more phase transition at T star, and it breaks the chirality. So how inversion symmetry can be broken? In order to understand CDW chirality in CDW, we just made a simple model. We know that the CDW is induced by charge fluctuation between gamma points and L points. So we consider the charge density wave along the 3 L vectors in first Brillouin zone. First, these are plane waves in first Brillouin zone. And first, we can consider the case that the 3 phases are all same. And then we can pull up the CDW data like CDW intensity like SSM image, like this. And these 2 images indicate 2 layers in the 2 by 2 per lattice. It makes a chiral CDW. You can see the mirror, you can see the blue line, and you can see that the mirror image by the blue line is identical to itself. It means that it's a chiral. So to break the chiral symmetry with LCDW, the phases should be different. This is the images made by 3 different phases. If you see the figure at the center, the blue line, which was the mirror plane of achiral CDW, is not mirror plane anymore. Below the blue line is brighter than the above. And also you cannot find other mirror planes or inversion centers in this case. So with the different phases of LCDW, we can make chirality. But however, unfortunately, this simple model cannot explain everything. There is another problem, which is that the symmetry of lattice and charges are different. A previous slide, we create a chiral CDW with different phases. Let's bring the same argument to the lattice. We can sum photon eigenvector at 3 L points with different phases. And of course, because lattice displacement cannot be imaginary, we need to take real part. Then it cannot break inversion symmetry. Also, any combination of L photons cannot break inversion symmetry of lattice. Then this is the problem because it's contradictory to Newman principle, which means that the physical property of materials must be the same with the symmetry of the lattice. So therefore, another displacement should be considered to break the chiral symmetry in the lattice. We would say that it's M photon mode. According to the DFT done by Alaska, the photon instability is expected to along the LM direction. They have negative energy. Therefore, it's natural to think of displacement along the M points like L photon, and it can break chirality. The right table, possible space group from the combination of L modes and M modes are calculated, and the 3 indexes here is the displacement along the phonon eigenvector, for example, M1, M2, M3. I highlighted the chiral group in blue, and you can check that M displacement is necessary to break the chirality. So therefore, our research focused on finding M displacement. Can phase transition at 200 Kelvin induce M displacement? If we suppose that M displacement is caused by second order phase transition, then it's impossible according to the Ginzburg-Landau theory. According to the Ginzburg-Landau analysis, generally a second order phase transition should be involved with order parameters of only one irreducible representation. In our case, because L phonon modes and M phonon modes have different irreducible representation, L and M phonon cannot condense simultaneously. So in our current theory, 2 second order phase transition is needed to make chirality, which seems to be consistent with the observation from photocurrent measurement. However, in our research, we couldn't find any evidence of additional second order phase transition below known critical temperature. So we find to find evidence of additional phase transition, we performed inelastic X-ray scattering. We did our experiment at Advanced Photon Source sector 30 with 1.5 milli-electron volt resolution. Although the layered materials are easy to band and generally the domain size is very small, the small spot size of X-ray make it possible to follow one grain. Right figure is the photon dispersion that we measured, and it was very successful. And here are our observations. Generally, photons have very long lifetime, and the photon spectrum should be the same with the instrumental resolution, like elastic signal at 0 energy, the gray area. However, L phonon in the orange color have very broad line shape from room temperature to the critical temperature. It's likely because L phonon is coupled with charge fluctuation, and the energy of L modes goes to 0 at critical temperature 200 Kelvin. These are consistent with the earlier measurement. And for M modes, it also heavily damped like L modes, perhaps because of the same reason, but it remains finite energy near 175 Kelvin, where additional phase transition is expected to happen. We can find clear shoulder at 170 Kelvin data. It means that M phonon does not condense. One can ask a question that, what's the big elastic peak in 170 Kelvin data? It's a break peak because M points become zone center after phase transition. It is all out peak, but it's a very small break peak. So anyway, it's not condensation of M phonon. So let's go back to the scenario that M displacement is induced by the second order phase transition. The second order structural phase transition must involve phonon condensation or anomaly of zone center phonon, acoustic phonon. So there is a scenario that M phonon condense like L phonon and induce the displacement, but we just confirmed that there is no M phonon condensation. You can find clear shoulder at 170 Kelvin data, which is already below T star 175 Kelvin, and it does not disappear up to 150 Kelvin. And the phonon dispersion measured near M points also indicate that there is no phonon condensation. What could be other possibility to induce phase transition? How about acoustic phonon? When shape of unit cell is changing through the phase transition, it can be shown as softening of zone center acoustic phonon. It was not our original scenario, but it could be. So right figure, our phonon dispersion measured at 200 Kelvin and 180 Kelvin. The slopes are the same in gamma points. So there is no anomaly in the zone center. So we can say that there is no 2 second order phase transition. Then what could be the origin of chirality? To reveal that, we measured M phonon temperature dependence. Damped harmonic oscillator model was used for fitting because L and M phonon are heavily damped. Here we plot the fitting parameter. Left figure is phonon energy and right is a lifetime broadening depending on the temperature. It means that the width of Lorentzian line shape. If we look at the phonon energies, you can check one more time that M phonon does not condense at any temperature. It is often until T star and harden upon cooling. And the interesting thing is that the lifetime broadening gamma of endpoints increases below critical temperature, which means that endpoints start to couple with something below critical temperature. So then what could couple with M phonon? It's natural, obviously it's natural to think of CDW order parameter and L displacement because they become non-zero below critical temperature. And if we consider this coupling, we can explain chirality using Landau analysis. The combination of rho, L, and M can be determined in Landau free energies if it is invariant under the symmetry operation. And this term can be an example. So the threefold rotation permits indexes 1, 2, 3, 1, and this permutation does not change the term. And for inversion operator, rho become even and L and M become odd. So product of 3 become even. So this term is invariant under the inversion symmetry. It also invariant under other symmetry operations. So we can consider the additional term in Landau free energies, and this term can induce M displacement when L and rho become non-zero. This is how inversion symmetry is broken in 1T titanium diselenide. And also we found the forbidden CDWP that can only be explained by M displacement. For this peak is forbidden under the known structure P3 bar C1. Therefore, this is another evidence that atom moves along the M phonon eigenvector. So even if M phonon does not condense, M displacement is induced below critical temperature, and 1T titanium diselenide become chiral immediately below known critical temperature, 200 Kelvin. Let me summarize my presentation. In order to break chiral symmetry, M phonon displacement is necessary. However, we cannot find chiral second order phase transition below non-critical temperature. So instead, M phonon displacement are induced below critical temperature by coupling with rho and L. So in conclusion, chiral symmetry breaking in 1T titanium diselenide is due to incompatible symmetries of charges and lattice sectors. And this is end of my presentation, and thank you for listening.
Great, thank you. So again, maybe we should continue with our next speaker. Next speaker is Anisha Singh from Stanford University. Actually, Anisha is our official last user at the Sector 30, and she spent the time over the weekend, almost 24 hours, and she was introducing the new capability for IXS measurement, namely phonons under uniaxial strain. Please, Anisha, go ahead.
Thanks for the introduction. Yeah, I was very lucky to get some of the last photons out of Sector 30. Let me just share my slides. Okay, and then this is the presentation mode. All right. Yeah, so as Amit mentioned, I'm going to be talking a little bit today about how we've been working on developing capacity for in-situ strain tuning for IXS measurements. This is still very much a work in progress, but I'm happy to share some of the preliminary data that we've taken from these measurements so far. So I'm going to start a little bit with just some sort of high-level motivation for why we're interested in strain tuning and how we actually do it. And then I'll get into a specific case study of one of the materials that I've been looking at with strain. Okay, so to get started, why are we interested in strain? So as a lot of these talks have touched upon, symmetry plays a very integral role in dictating the electronic properties of crystalline solids. And often we see with electronic phase transitions, there is some associated reduction or breaking of symmetry that happens. And so if we apply strains that break the same symmetries, we can actually very well probe these phase transitions. So a very common example from the world of physics I'm in is an electronic nematic phase, which is characterized by spontaneous breaking of fourfold rotational symmetry. So if we apply this very sensitive probe of symmetry with X-ray techniques, this presents a very powerful way to explore complex relationships between electronic and structural orders in different types of material systems. So practically, how do we actually do in situ strain tuning? So generally, we use a class of sort of commercially available strain cells, which are made by a company called Razorbill, and they're compact and designed for cryogenic applications, and they consist of a series of piezoelectric stacks to which we can apply voltages to dynamically change their extension or compression to both apply tensile and compressive strains. And particularly for the work that I'm going to be talking about today, while we're moving into trying to apply strains to more layered quasi 2D materials, rather than mounting the sample directly into the jaws of the cell, as is shown in this schematic, we're actually going to mount the sample onto the substrate shown here in sort of this neck region of the substrate, which is going to allow us to more reproducibly and robustly strain our sample through repeated strain cycles, while maintaining the crystallinity of the sample that you need to perform X-ray measurements. All right. All that being said, though, there are still a lot of technical challenges that we had to consider as we start integrating strain tuning into IXS measurements. So this is a really interesting way to now probe lattice dynamics and how that evolves as we apply strain. But one of the main challenges, again, as I mentioned in the previous slide, as we're working particularly with very thin, very mechanically delicate and soft samples, sample quality is going to be a big issue. So these samples already don't have great crystallinity, and it's just going to get worse, right? As we repeatedly strain the samples, we're going to see a broadening of our Bragg peaks, and ultimately is going to result in an increase of our elastic line. Also, as we're working with a small beam, and as we're constantly moving our sample with strain, it's a bit non-trivial, right, to maintain consistent sampling of our crystal volumes, and to keep in mind as we're taking these measurements. Something else that I want to touch on is the way that the sample is actually mounted within the Razorbill cell. There's a series of screw plates that we have to use to actually fix that substrate, which I showed on the previous slide, which is going to result, especially when you're working in transmission geometry, a sort of reduction of access to our sample from the beam. Something else that we had to sort of contend with. And then finally, there's sort of competing interests in terms of what the ideal sample dimensions are for what's going to give us high and homogeneous strain transmission into the sample, and then also what's an ideal sample for working in a transmission geometry. So for homogeneous and high strain transmission, we're going to want a sample that has a relatively thin height, and there's minimal strain relaxation through the sample. And then we're going to want a sample that's a bit wider. In that sense, the strain throughout the sample is going to be, again, a lot more homogeneous, and then it's going to remain coupled to the strain that we're applying to the substrate. Both of the things are a bit opposed, though, with what we'd want for a transmission geometry measurement. Obviously, there we're going to want a more narrow sample to reduce the attenuation of our signal. And then it's easier, obviously, to work with a sample that is thicker. So balancing both of those sort of restrictions on sample dimension that we had to be thinking about as we prepare samples for this measurement. All right, so the example material I'm talking about today are the rare earth tritellurides, and specifically I'm going to be talking about how we can use uniaxial strain tuning to manipulate the charge density wave order in these materials. So the rare earth tellurides exhibit unidirectional in-plane charge density waves. And just a quick note on nomenclature here. So for us, the in-plane axes are actually going to be labeled as the A and the C axes. Now, overall, this material family has a relatively simple phase diagram. Specifically, we're going to be focusing in our measurements on erbium telluride. And as you can see, for the heaviest members of the rare earth series, these materials actually have a series of CDW transitions. So actually there's a secondary order, which corresponds to CDW order running orthogonal to the primary order, so CDW along the A direction. But for the purposes of everything I'm going to be talking about here, we're really just going to be focusing on this higher temperature transition, which in erbium telluride happens at about 268 Kelvin. Now, the system also has a glide plane, which results in the material being very weakly orthorhombic. But as a consequence of the orthorhombicity, we see that the primary CDW wave vector is always going to run along the longer of the two in-plane axes, which in this case is that C axis. All right. So there have been some previous IXS measurements that have been done on this material family, but statically, not with the application of strain. And interestingly, what we see in those measurements, as we approach the CDW transition in these materials, we see a softening of a phonon mode at the CDW wave vector. But we see that softening actually along both the C and A directions, although the phonon mode then softens completely along the C direction, where we see the CDW transition and long range CDW order take place. Nevertheless, these observations are indicative that, above CDW transition, CDW fluctuations are fairly isotropic from the two directions, and suggest if we could reverse this anisotropy in this crystal, it may in fact be possible to reverse or reorient CDW wave vector in the material. And say we could do that by applying uniaxial strain. Now, when we talk about strain tuning in the rare earth telluride crystal family, it's a bit non-trivial what the effect of uniaxial strain will be. And this comes back to that glide plane that I mentioned in a few slides ago. Now, because of this glide plane, that's a symmetry operation that does not couple to strain. No amount of strain can ever undo that glide plane. So even at the point where we strain tune the system through the point where the in-plane lattice parameters are equivalent, the system is still fundamentally tetragonal. The system still knows those two in-plane directions are different. It gets a little bit more interesting, though, if we think about how the charge density wave order might couple to strain. So if we admit terms into a free energy expansion that allow for a coupling between CDW order and uniaxial strain, the simplest phase diagram that we can draw is shown on this slide. And what we can see is that indeed we can flip between CDW order along the C axis versus the A axis as we apply uniaxial strain. Most interestingly, this also reveals that there indeed is a bicritical point where the phase transitions between that C axis CDW order and the A axis CDW order coincide. So at this point, we expect an identical vanishing of the coefficients of our quadratic order parameter terms in a free energy expansion. And the remaining terms, at least up to quartic order in our free energy expansion, are actually going to be invariant under switching of the A and C axes, suggesting that at or close to this bicritical point, there actually is an emergent tetragonality in our system. Okay, so that's all good and well. We can write this model down, but there are a few things we actually need to demonstrate to show that this is indeed true. And I want to share a little bit about these other things that we've observed in this material through the application of uniaxial strain, starting with some extra diffraction measurements that were also done here at the APS at sector 6. And so also diffraction is a very powerful tool to study this material because it provides a direct probe of the charge density wave order material by observing the superlattice peaks and how they evolve with strain. And what these measurements show is that the CDW order indeed responds to strain and the primary CDW wave vector can be reoriented. All right, so on this slide, I'm just showing measurements of the CDW superlattice peaks that were done in the material, while different values of uniaxial strain were applied to the material. So for all the measurements I'm going to be showing today, we're going to be talking about strain applied to the A-axis of the material. So in this case, we're applying tensile strains to the A-axis of the material, which effectively is reversing the sort of inbuilt anisotropy of the system. So what you can see, starting looking at the darkest curves on this plot, is we see a CDW superlattice peak along the L direction and nothing along the H direction, which is exactly what we'd expect, consistent with the CDW order being along the C axis. As we increase the tension that's applied to our sample, though, we see a suppression of that L axis CDW peak, corresponding with the emergence of a CDW superlattice peak along the H direction. So indeed, it seems to suggest that the CDW wave vector can be reoriented by 90 degrees with the application of uniaxial strain. All right. We've also been able to study this material under strain with different transport measurements, specifically looking at the anisotropy in the in-plane resistivity and the in-plane elastoresistivity. And particularly, these measurements have showed us that there is some intermediate strain state where we actually see the elastoresistivity response of our sample is maximized, which at this point would correspond to a divergence in our max stability, which is consistent with what we'd expect to see with an emergence of a fourfold symmetric state in our system, or at least a fourfold electronically symmetric state in our system. All right, so on this slide, I'm just plotting the in-plane resistive anisotropy as a function of temperature for different offset strains. And what you can see is that as we pass through the CDW transition, which again is at about 268 Kelvin, the resistive anisotropy flips between positive and negative values, depending on which axis is hosting that CDW order, which we can control by strain. So consistent with what we sort of see in our XRD data. And then promisingly, this measurement reveals that there indeed is some intermediate strain state through which, when we cool through the CDW transition, the anisotropy associated with the CDW transition disappears. So such that there's an equal amount of CDW order in both directions. And then finally, just showing that elastoresistivity data. So here we have our transverse elastoresistivity, so the sort of anisotropy of the in-plane elastoresistivity plotted as a function of applied strain for a series of different temperatures. And we see indeed there is an intermediate strain state where we see a maximized response consistent with sort of the onset of some fourfold symmetry. And this observed critical strain state is similar to what we saw on the previous slide, where we see this resistive anisotropy disappear. Okay, so all to say, there's lots of reasons to be interested in studying this material under the effect of strain. And because it really was these IXS measurements that motivated this strain work in the first place, it seemed a fair point to come back and see how the phonon dispersion is changing now when we apply strain. So particularly, we want to see if this rotated CDW has a similar behavior as its unrotated analog. So is the rotated CDW really just a 90? Does it look exactly the same, rotated by 90 degrees, or something fundamentally different about this CDW order in the orthogonal direction? And this would help us understand better what the capacity of any actual strain is in this material to indeed restore the rotational symmetry of the material. And then more broadly, this might provide additional insight into the nature of the charge density wave order in this material family. All right. So to get started, so for an initial experiment, we had a relatively simple hypothesis. So if we, again, are still applying tension along the A-axis, and we're looking at the CDW, or sorry, the phonon mode at the CDW wave vector along the C direction, we expect to see a hardening of that phonon mode and a softening of that same mode when looking along the A direction, corresponding to this reorientation of the primary CDW wave vector in the material. Okay, so on this slide, I just have sort of an example of a spectrum that we collected. And in it, you can see a lot of the issues that I pointed out in the very beginning of this talk. So this was for measurements in when, again, we are measuring along the C-axis while we apply strain along the A-axis. And this is not quite at the CW wave vector. So the CW wave vector is about 0.3. So we're just looking a little bit off that Q value at 0.275. And so you can see, yes, these scans reveal that we have a fairly large elastic line, and overall our counts are low, probably due to that fact that I mentioned that the sample dimensions that we're working with are not quite optimized for large transmission of our signal. Okay. Nevertheless, we're still able to extract dispersion of our phonons that is relatively consistent with what is seen for other members of the rare telluride family that have been previously measured. So no data had been previously taken in this particular urban telluride, but it has been taken in other materials like turbine telluride and dysprosium telluride. And so we see the general behavior between all of these members of the crystal family is quite similar. So the choice of rare earth ion really doesn't have a large effect on the phonon dispersion. Okay, so once we've established this, that we're looking at the right thing, we want to start applying some strain now and see how things change. So I'll start off with the less interesting bits, which are these higher order modes. And we see that in general, these modes are not really evolving in any kind of systematic way as we apply strain. So on this slide, I'm still plotting things in terms of the absolute voltages that we apply to the piezoelectric stack. So here, positive voltages are going to correspond to positive strains, so tensile strains. But we can also observe how the lattice is responding through the application of these voltages and then convert these into real strain values. So the rest of the data will be plotted in terms of those real strain values. So yes, there is no clear change in the dispersion of these phonons with the application of strain. There was some intensity changes in these modes, but again, like I mentioned, these are a bit more challenging to interpret because it is hard to guarantee that we're actually maintaining a consistent sampling of our crystal volume. So since this isn't happening in a very systematic way, it's challenging to put too much meaning into that observation. Okay, so finally, we can take a look at what's happening to that soft mode. So here I'm plotting a series of scans that were taken at the CDW wave vector for different values of applied strain. And we can see that there is some intensity that is moving to higher energies. And we also see that as we apply more strain, the intensity that we're seeing is going down, and that's primarily because the diffraction peak associated with the CW wave vector is actually being rotated, right? So we're losing intensity at our elastic line. So we can fit this to a series of modes, and we see that indeed that there appears to be some hardening of the phonon mode at CDW wave vector. So we were very excited to see some change in the data as we apply strain and affect the CDW in this material. All right, so this seems to suggest that if the soft mode that we're measuring is indeed hardening as we apply tensile strain, that the rotated CDW phase sort of seems to be behaving just as 90-degree analog of the primary state, the unrotated CDW wave vector. Now, this is not quite the complete picture, since we have not conclusively observed the corresponding behavior along the A-axis, right? So we would want to see softening of that same phonon mode along the A-axis as the CDW order is reoriented along that direction. Like I mentioned very briefly at the beginning of this talk, though, performing measurements along both the C and A axis simultaneously in the same sample is challenging, since because of the geometry of the Razor-Bill cell, we can't access both orthogonal directions in a single sample because of how the crystal is mounted. There are some screw plates then again block the beam. So really looking ahead, things that are interested in is how we can really improve this sample environment and also sample quality, things that we can do to still maintain robust strain of our sample while maintaining sample crystallinity. And then what are changes we can make to how this sample is mounted within the strain cell to increase sort of the angular axis that we have to our sample, so we could actually perform both measurements of both in-plane directions in a single sample. And so yeah, and then also things that we can do to more reliably maintain consistent sampling of our crystal volume. These are all things that we have to think about, particularly in how the sample is prepared and mounted to better perform these experiments in the future. Yeah, so that's all I have for now. Thank you, and I'm happy to take any questions.
Thank you, Anisha. Okay, so now next move on to next talk. Actually, we are going to switch from the momentum resolved IXS measurements for phonons to NRS measurements on thin isotope. And our next and last speaker is Wenli Lee from University of Alabama at Birmingham. Please go ahead, Wenli.
Hi, do you see my screen?
Yes.
Okay, it's the full screen, not the small one, right?
Yes.
Okay, all right. Okay, thank you, Ahmed, for the introduction. And I want to thank Michael for the invitation to talk about this work we have done recently. This is still work in progress, and we have finished. I believe we have finished all the experimental work, and now we just trying to collaborate with theoretical groups and try to understand our experimental observations. My name is Wenli Lee. I'm an assistant professor at the Department of Physics at the University of Alabama at Birmingham. This work here, well, I changed the title slightly. Originally, I had a magnets with a plural, but after looking through the data, I thought it's better just to focus on the single system to show this capability of the beamlines. This work is supported by the University of Alabama at Birmingham and also National Science Foundation. Okay, see where I can progress. All right, so before we get started, I want to first give you some introduction of this specific compound. It's called the Kagome magnetic metal. So in this compound, there are two iron Kagome layers separated by a thin honeycomb spacing layer. And when you cool down, if you go very high temperature, cool down below 650 Kelvin, the system becomes ferromagnetically ordered with a canted moment. And the magnetic moment in this case is 1.9 μb per iron atom. And so the crystal structure, the unit cell is trigonal, is R3M. And so previous calculations and also later on observed experimentally shows a very interesting band structure. It's shown here. You can see my mouse. So the interesting thing about this compound is there are two Dirac bands across the at the K point, and also a very flat band across the whole Brilliant zone. And that's pretty unusual. That's coming from this unique Kagome lattice. So especially this flat band that's coming based on this model here, it's because this specific Kagome lattice, this allow the, so on this Kagome lattice here, you have the block wave function alternate the sun across the 6 vertices on each of the hexagon, and that lead to destruction of the interference outside the hexagon. And that give you this flat band across the whole Brilliant zone. So the interesting about this system, because the unique band structure, it shows very large anomalous Hall effect, and also ordered at very high temperature, probably one of the highest metal Kagome material with the highest magnetic ordering temperature. And when you cool further down, there is a spin reorientation. In another paper, they reported a spin glass transition from out of plane to in plane. When you cool down from high temperature to low temperature. And some studies show that it's possibly associated with a spin phonon coupling that's shown at the A1G mode around a 10 millielectron volt. So that's done previously from a Raman experiment at low temperature. And also there are some calculations show that the system is extremely tunable. So the spin orbit coupling and the band structure is extremely tunable, and also has a large dependence on the magnetic ordering magnetic configuration. So motivated by this series of work, and we applied pressure. Hopefully we want to control the magnetism, crystal lattice, and also look into the electronic and the band structures. Okay, so that's why we chose nuclear resonance scattering technique, because in this system is so convenient. It's iron tin, and iron both elements have Mossbauer active isotopes. So it's really an ideal technique, this nuclear resonance scattering ideal technique to study this system in terms of the magnetic transitions and lattice dynamics. Okay, so I think most of us are familiar with this setup here. And I just want to mention, so we have done this experiment at the sector 3 and the sector 30. Sector 3 on iron 57 and the tin 119 at the sector 30 with Michael. And with this single technique, we can actually get the information on the magnetism on iron, and also look at the transferred field on the tin side. And also we can collect the data, the Enrix data, and tell information on the element specific phonon density state. Okay, so here I want to first show you the this is one of the 3 rounds of iron 57 synchrotron Mossbauer experiments at room temperature. And we just load a piece of single crystal in a diamond cell, and we loaded pressure medium, different types of pressure mediums. One round we use a neon, another round we use methanol, ethanol 4-to-1, and also the third round we didn't use any pressure medium because we were doing Enrix experiments, and simultaneously we could collect data for the synchrotron Mossbauer. So here, this round is on a natural sample taken at the room temperature under compression. So you can see here, as you increase the pressure, the oscillations are suppressed. So that's an indication of suppression of magnetism. And this just show the red curve here are just a very preliminary analysis using one single iron site. And by feeding this data in conus, we can extract the hyperfine field, how the hyperfine field is changing with pressure. So above 21.5 GPa, so roughly based on the 3 different runs, we observed above 23 GPa, we see a suppression, a collapse of magnetism, collapse of magnetic order. And again, this is taken at the room temperature. And also this critical pressure, 23 GPa also, it's insensitive to pressure medium. So whether it's neon hydrostatic or quasi-hydrostatic or non-hydrostatic, we always see a transition collapse of magnetism above 23 GPa. Okay, we also did synchrotron Mossbar measurements on tin 119 at different temperatures and pressure conditions. And this data here is just an example of how the tin data look like. This is the enriched, fully enriched, to some extent enriched iron 3 tin 2. This data was taken at the room temperature, and just feeding this data, we used a 2-site model because based on this iron tin, the crystal lattice, there should be one tin site, at least one tin site in the iron tin layer, and a separate tin honeycomb layer. So just based on this model, we can feed the data reasonably well. This is just a very preliminary analysis. And we compare with the earlier measurements that's done in the lab using a radioactive source, and the parameters are roughly agree. And we have a series of data, and the analysis is in progress. Okay, so to understand the suppression of magnetism in iron site at room temperature, so we want to look at whether we want to know whether the magnetic order temperature is just decreased by applying pressure to drop the below room temperature, or is just the magnetic moment is completely suppressed. So to understand this point, we loaded a sample and put in a cryostat and cool down and look at the Mossbar, take Mossbar data at the different temperatures and pressures. So in this case, early on, we've been using this cryostat originally designed by Stas from DAC Tools. And because there is some malfunction on this cryostat, we quickly switched to a new cryostat, again made by Stas from DAC Tools. And we were able to cool down and took a series of data at the different temperature and pressure conditions. And we found out that the critical pressure at the low temperature is where the magnetism is suppressed, is slightly higher temperature, happens at higher pressure. So that's kind of counterintuitive because temperature itself is acting like a pressure effect. So here we observe the suppression occurs at the slightly higher pressure. Okay, so next let me move on to ENRICS. So to take ENRICS data, first of all, we used a enriched sample. So the sample were made by Robert Cava's group from Princeton University, and also later on by Wei Xie's group from Michigan State. So with the enriched sample, we can enhance the counting rate and reduce the counting time significantly. So we just need to have a cell that has a large window on the radial direction and place the detectors next to the cell, and to reduce the distance and increase the angular access to the signals. And so in this case, we in one of the runs, we use a miniature panoramic deck with 2 APD detectors placed next to the sample. And in this case, because the signal is coming out of the gasket, so we use a beryllium gasket with a cubic boron nitride insert. This insert is to increase the thickness of the gasket and also maintain a decent thickness on the sample. Okay, so we got up at room temperature again. This data is taken at room temperature, and we increase the pressure and repeat the scans for several times at each pressures. And then this is the NRIX data we get, and we can derive the density of state. In this case, it's done at the sector 3 ID on iron 57. So here, this is the derived phonon density of state specific to iron element. And we observed a continuous hardening of the phonon modes. And for the detailed analysis of the each of the evolution of each of the phonon modes, we need to look at the data more carefully. Okay, and then we also did tin NRIX experiments at the sector 30 IDB with Michael. We first took a piece of single crystal sample and put it in the beam, and again, this is enriched sample, so the count rate was really good, and this was done at on a very large crystal, and we can get the phonon density state on the tin side. And then we cool down at low temperatures. I think in this case, we didn't use a focused beam, so very large beam. We stacked several crystals on the holder, and we just cool down and collected data. So then we found out there is some inconsistencies in several spectrum because we cool down the sample holder also changed position, and it's a unfocused beam. So it depends on which crystals you are hitting. And we saw there is some variation on some phonon mode around the 5 milli-electron volt. Okay, and then so we collected data at several temperatures, and that the inconsistency is there. And in a separate run, we used a large single piece of crystal, and we didn't see an obvious phonon mode around the 5 milli-electron volt. So to look into that inconsistency there, we took the same piece of crystal we have studied earlier that shows these pronounced phonon mode around a 5 milli EV. We did SEM, and we found out there is a excess of tin on the surface, mostly on the surface. So we concluded, we contacted our sample girl, and they mentioned there could be excessive tin because the sample was made using tin as a flux. And then we look into this paper, also done on NRIX, and this is beta tin, the phonon density of state at the low temperature, and there is clearly a mode around the 5 milli-electron volts. So we conclude that this inconsistency here around a 5 milli-electron volt could come from the excess tin on the samples that we studied. So then later on, we just every time we load the sample to study phonon magnetism, we try to screen the single crystal ahead of time and to make sure the purity. And then this is one of the run. We loaded a purer crystal in a dynamic cell and did tin NRIX experiments under high pressure up to 30 GPa. And again, we consistently see this shift of the phonon modes becomes hardens. And also, if we compare the, if we include also our iron data and compare with the tin and the iron specific phonon density state, and we notice this this phonon mode here above 30 millielectron volt on the tin corresponds to, we concluded it corresponds to the vibration mode coupled with iron. So that means this mode here is coming from the iron tin Kagome layer. And also we compare with the previous calculations done by this paper here on the specific phonon density state on tin and iron, and the agreement is excellent. Just if you do a simple conversion on the frequency into millielectron volt and the cutoff frequency, and all the major modes are there. Okay, and then we ask ourselves what happened to the crystal structure, and what's causing this suppression of magnetism, and whether this Kagome lattice motif is disrupted under pressure, and that could be causing the suppression of magnetism, because the magnetic state is likely very heavily impacted by the flat band in the band structure mentioned earlier. So we did several rounds of X-ray diffraction experiment at the 13 BMC, and we found out above 23 GPa also, it's pretty consistent with the suppression of magnetism at room temperature. And we found out there are some peak splittings, and there is definitely a crystal structure transition is going on, and that coincide with the collapse of magnetism. And then we noticed there's an earlier paper from 2006 also reported. So in this work, they did systematic studies on several compositions of iron tin systems, and they did high pressure measurements on several compounds, and they reported also a similar peak splitting and crystal structural transition under pressure that's very close to our the pressure we observed. However, they didn't identify the high pressure phase. So then we worked with Yan-Sun Yao's group to identify the high pressure phase. So he did some structural search, and we found out this C2M phase, one of the C2M phase could be a possible candidate for the high pressure phase. And if we, this is just a fit with the proposed C2M based on the calculation, and the fit is reasonably well. So this proposed crystal structure, if we look at the crystal lattice, we concluded that if this is the real high pressure phase, the Kagome lattice is disrupted, and that could be the reason that's causing the suppression of magnetic order. Okay, so the next we're gonna analyze the Mossbar data on both iron and the tin, and to look at this exchange interaction. Hopefully we provide some information on the magnetic configuration and the exchange interaction, and also look at this high pressure crystal structural phase more carefully. And our collaborator plan to do some band structure calculations to provide insight on the evolution of the flat band, and also the Dirac bands under after the phase transition. And also we want to analyze in detail how this flat band, the changes in the flat band is has any impact on the suppression of magnetism. And also we have planned to do this, phonon calculations to understand the change of the lattice dynamics and the correlation with the magnetic order. Okay, so my my last slide, I want to acknowledge my group, the graduate students, undergrad, Trenton Coverhouse, and also my postdocs. And also, most important, I want to mention that I really appreciate all the support from the beamline scientists, especially during the COVID time. I started my group in 2019, and shortly after that, the COVID started. And so a lot of the experiments actually were done remotely with great support from the beamline scientists. Okay, so, and also I want to thank Bob Kava's group from Princeton, Wei Xia's group from Michigan State to make the very high purity iron tin samples. And also the Siri group, Yanshun Yao, who have done the calculations to identify the possible high pressure phase. With that, I want to thank you, and I will be happy to take any questions.
Thank you, Wande. So actually, we are at the end of today's workshop, and I would like to thank all of our speakers today. And also, I would like to remind that our iXScience Group's workshop will continue tomorrow morning for the RIX program, and they are going to start at 8:45. And now floor is open to questions and discussions. And I guess except Mingda, and I don't see Oliver, all our presenters are still here with us. If you have any question, please feel free to ask your questions or any discussion. We have still like 10-15 minutes. We can go ahead. So maybe actually, I want to ask all our speakers whether with the new source, whether we can take any advantage of studying in a non-equilibrium state, like also we did in the localization and unharmonicity, whether the new source might couple to this, like the coherent fraction of the beam, might couple to this phenomena that might produce some sort of spurious peak in our energy excitation. Whether you have any idea, at least we have a year to think about it, and maybe if we come up with any good ideas, we can entertain those experiments at the science commissioning part.
I have a quick question to Anisha. Are you there, Anisha?
Yeah.
Yeah, you are. So you showed some interesting strain measurements. Is the same setup suitable for compression as well, or is it just for tension?
Yeah, so actually the measurement that I did over the past weekend was on the other strain polarity, so applying compression as well. You know, because we are working with relatively soft materials, there is some risk of sample buckling. But as far as we could tell, we didn't have any evidence of that in the measurement. I was still able to see the lattice compress. So yeah, it works in both directions. In this particular case, although we aren't working at very cold temperatures, with this particular sample, because of differential thermal contraction, you kind of are biased towards tension. But in general, yeah, you can work at both directions, compression and tension.
Thank you.
Yeah, of course.
Okay, I have a question about this energy domain experiment on the synchrotron, synchrotron Moss bar. I think Tom mentioned that the sample would be moving, mounted on the Doppler drive, I guess. So is that still compatible with low temperature sample environment or high pressure? With the diamond cell in there, or with a cross-stat in there, are we still able to do measurements in energy domain?
The sample is not on a Moss power drive. So
the sample is not, because I only heard a part of your talk yesterday.
Yeah, that's okay. Yeah, the emitter that generates the gamma rays is on a MOS power drive.
Okay.
The sample is in the same location as you would expect for other samples. You just have to be
Okay.
concerned about motion along the beam direction. So vibration.
Oh, I see.
If you
Okay.
mount your sample on a cryostat, you have to know sort of the vibration dynamics to determine whether or not there's velocity motion along the beam.
Well, if it's a closed cycle, yeah, there's a concern. But if there is no vibration motion on the sample, it should be no concern, right?
As long as there's no motion on the sample, yeah, no velocity. It's the
Okay.
velocity that matters, actually.
Right. Yeah. Okay. Thanks.
Ahmed, are you muted?
Yes, I am. Actually, yeah, I was just telling if there is no question, maybe we can conclude the session. And as a last word, I can just say that we hope to see all our users in person next year, and we'd like to continue supporting your exciting projects. And thank you for attending today's meeting.
Yeah, thank you all.
Thank you. Bye.
Thank you, Ahmed. Take
Thank
care.
you.
Bye-bye.
Bye.
Bye-bye.